Hello, friends. Welcome back. Tonight, the sky holds a secret, something ancient, something that doesn't belong here. A traveler older than mountains, older than oceans, drifting through darkness for billions of years. It came from a place we'll never see, carrying messages we're only beginning to read. And right now, as you listen to these words, it's passing through our solar system for the first and final time. This is the story of 3I Atlas, the third interstellar visitor we've ever witnessed. A comet from another star system, from another time, gliding silently past our sun before vanishing forever into the void. Some things only happen once. Before we drift into this quiet journey together, if these stories bring you comfort in the stillness of night, you might like to stay a while. You can gently tap the like button, not for algorithms, but as a small light in the darkness, a way of saying you were here. Subscribe if you'd like more whispered truths about the universe, and ring that little bell not for noise, but so the next peaceful night can find you again when you need it most. Thank you for being here. Now, let's begin. Imagine this July 1st, 2025, a telescope in Chile, perched high in the Atacama Desert, where the air is thin and the stars breathe clearly, captures something unusual. A faint smudge of light moving against the fixed pattern of distant stars. At first, it seems ordinary, just another icy wanderer circling our sun, perhaps one of thousands that trace their ancient paths through our cosmic neighborhood. But then, the numbers come in. The trajectory calculations, the orbital velocity. And the astronomers realize something that makes them pause, that makes them look. Again, this object isn't circling anything. It's not bound to our sun's gravity. It's moving too fast on a path that curves open what scientists call a hyperbolic trajectory. A trajectory that comes from somewhere else and leads somewhere else, never closing, never returning. This visitor isn't ours. It never was. They name it 3I Atlas. The I stands for interstellar. The 3 means it's only the third time in all of human history that we've detected an object from beyond our solar system passing through our celestial neighborhood. The Atlas Survey Asteroid Terrestrial Impact Last Alert System spotted it first, a testament to our growing ability to watch the darkness and recognize what doesn't belong. Think about that for a moment. 3 times. Only 3 confirmed visitors from the vast ocean between the stars. The first was Oumuamua in 2017, a tumbling mystery that sparked 1,000 questions and just as many theories. The second was 2I Borisov in 2019, more familiar comet-like behaving, as our expectations suggested an icy wanderer should. And now, 3I Atlas. Each one a messenger carrying encoded within its ice and dust, the chemical signature of stellar systems we've never seen. We'll never see systems that may be dead. Now their light still traveling toward us across unimaginable distance. When 3I Atlas was discovered, it was already inside the orbit of Jupiter, roughly 410 million miles from our sun, traveling at approximately 137,000 miles per hour. To put that in perspective, if you could somehow stand on this object, you'd cover the distance from Los Angeles to New York in about 20 seconds. That's not the speed of something gently falling toward the sun. That's the speed of something with momentum built over eons, something that has been moving through the galaxy for longer than complex life has existed on Earth. Scientists suggest, based on the comet's velocity and its relationship to the random motions of stars in our galaxy, that 3I Atlas is somewhere between 3 and 11 billion years old. You think about that span? 3 billion years ago, Earth was still in its microbial infancy, single-celled organisms, just beginning to experiment with photosynthesis. 11 billion years ago, the universe itself was less than 3 billion years old, still in its vigorous youth, forging the first heavy elements in the hearts of massive stars. And through all that time, through all those ages, 3I Atlas has been traveling. Not in a straight line, nothing in the cosmos travels straight, but in a long, slow orbit around the center of our Milky Way galaxy. Research shows that the comet's galactic orbit takes approximately 250 million years to complete, just one lap. That's roughly the time it takes our sun, and us with it, to make one full circuit around the galactic core. Pause with that thought. In all the time that 3I Atlas has existed, it has witnessed the galaxy rotate dozens of times. It has passed by other stars, felt the distant tug of their gravity, seen solar systems form and die. It may have originated in a stellar nursery that no longer exists, ejected by gravitational interactions, perhaps by a passing star, perhaps by a giant planet forming in that long-dead system, perhaps by something we haven't imagined yet. We don't know exactly where it came from. The mathematics of orbital dynamics allow us to trace its path backward, but only so far. After millions or billions of years of tiny gravitational nudges from passing stars, from the galaxy's spiral arms, from clouds of gas and dust, the original trajectory blurs into probability rather than certainty. What we know is this: it came from somewhere in the disk of our galaxy. It was born near another star. And then something happened. Something violent enough to give it escape velocity from its home system, gentle enough not to destroy it entirely. Imagine that moment if you can. A piece of ice and rock, perhaps, part of a larger body, perhaps formed in the outer reaches of another solar system where temperatures allow water and carbon dioxide to freeze solid. And then ejection. Maybe a close encounter with a giant planet whose gravity acts like a slingshot. Maybe a near miss with a companion star in a binary system. Whatever the cause, the result is the same. This small object achieves enough velocity to break free of its star's gravitational embrace and tumble out into interstellar space. And there in the void between the stars, it travels. The galaxy is not empty. There are clouds of gas, thin wisps of atoms floating between the stellar islands. There is radiation from distant stars, cosmic rays from ancient supernovae. There is the faint pressure of galactic magnetic fields. All of these things touch 3I Atlas as it drifts through the darkness, adding tiny forces changing its path by infinitesimal amounts. For billions of years, it might not pass close to any star at all. Space is vast, unimaginably so. Stars are tiny points separated by oceans of nothing. The probability of collision, even of close approach, is vanishingly small. And yet, eventually trajectories converge. Eventually, by pure chance, the comet's path and our solar system's path through the galaxy intersect. And that's what happened sometime in the last few years. 3I Atlas, traveling on its ancient trajectory, happened to approach our sun's gravitational well, at just the right angle, just the right velocity to be captured, not in orbit but in a hyperbolic flyby. Like a spacecraft performing a gravity assist, it swings around our sun, feeling the warmth of our star for the first time in its long existence, and then continues onward, its velocity altered, but its journey unending. Some researchers have calculated that 3I Atlas has traveled roughly 16 light-years from its point of origin, assuming a relatively straight path, which of course is an oversimplification, but gives us a sense of scale: 16 light-years. Within that radius from our sun, there are approximately 56 known stellar systems. Any one of them could have been the comet's birthplace. Or it could have come from a star that has since moved away, following its own orbit around the galaxy, now dozens or hundreds of light years distant from where it was when this small, icy body departed. There's something deeply moving about this isn't there. The idea that we're seeing a piece of another world, another time, another place in our galaxy. That for a brief window months, really just months out of billions of years, this ancient traveler passes close enough to our Earth that we can point our telescopes at it, capture its light, analyze its chemistry, and learn something about the universe beyond our small corner of space. It seems as though the cosmos occasionally offers us gifts like this. Not often, not reliably, but sometimes. A reminder that we are not isolated, that our solar system is part of a much larger ecosystem of stars and planets, and the debris between them. That chemistry and physics operate the same way everywhere, that the elements forged in stellar cores disperse and recombine and form new worlds, new objects wherever conditions allow. And what does 3I Atlas look like this visitor from the deep? From the images captured by the Hubble Space Telescope, it appears as a teardrop-shaped cocoon of light, not the comet itself exactly. The solid nucleus is far too small and dark to see directly, but the cloud of gas and dust surrounding it, heated by our sun, glowing softly against the black backdrop of space. That glow is the comet waking up. For billions of years, 3I Atlas has been frozen dormant, a solid lump of ice and rock at temperatures close to absolute zero. But as it approaches the sun, even from a distance of hundreds of millions of miles, the surface begins to warm. Frozen water starts to sublimate, transforming directly from ice to vapor without passing through a liquid phase. Carbon dioxide does the same. These gases escape from the comet's surface, carrying with them tiny grains of dust. And together, they form the coma, the fuzzy atmosphere that makes the comet visible. Hubble's images show this process happening in real time. You can see the plume of material streaming away from the nucleus, pushed by the pressure of sunlight and the solar wind. The background stars appear as streaks because Hubble was tracking the comet's motion, keeping the wanderer centered in frame while everything else moved past. It's a small thing, that detail, but it reminds us that we're watching something in motion, something that won't stand still for our convenience. Scientists estimate that the nucleus of 3I Atlas, the actual solid body beneath the glowing coma, is somewhere between 1,400 feet and 3.5 miles in diameter. That's a large uncertainty range, the result of trying to measure something tiny and distant, surrounded by a bright, obscuring cloud. More recent observations suggest the comet is probably on the smaller end of that range, perhaps less than a kilometer across. Similar in size to 2I Borisov, the previous interstellar comet we studied. Small then. A mountain in space. A city-sized chunk of ice that has been falling through the galaxy since before life on Earth learned to see. It's humbling in a way. This vast journey, this epic story, carried by something we could walk across in an afternoon if we could somehow stand on its surface. But size isn't the measure of importance, is it? What matters is where it's been, what it's seen, what stories are written in its ice. Every comet carries within it a record of the conditions that existed when and where it formed, the ratio of different isotopes of elements, the kinds of molecules frozen together, the mixture of rock and ice and organic compounds. These details tell us about the temperature and pressure and chemistry of the disk of gas and dust that surrounded the comet's parent star billions of years ago. They're like tree rings or layers of sediment archives of ancient environments preserved in frozen form. And 3I Atlas, being from another stellar system, entirely offers us something precious, a comparison, a way to see how the chemistry of other corners of the galaxy differs from our own. Are the ratios of elements the same everywhere? Do all stellar systems form the same kinds of comets? Or are there fundamental differences that reflect the history and composition of different regions of the Milky Way? These are questions we've asked but never been able to answer with certainty, until now. Until visitors like 3I Atlas pass close enough for us to study them, to point our instruments at them, and capture their spectra to see what elements are present and in what proportions. And already we're finding differences. Subtle ones, but real. More carbon dioxide than we typically see in our solar system's comets. Evidence of nickel surprisingly abundant. A notable absence of iron, or at least less than expected. These aren't dramatic differences. Comets everywhere seem to follow similar general patterns, but they're measurable. They tell us that the cloud of gas and dust that formed 3I Atlas's home system had a slightly different composition than the cloud that formed ours. Maybe that parent star was older, more metal-rich, having inherited material processed through previous generations of stars. Maybe it was younger, formed from more pristine gas with fewer heavy elements. Maybe it formed in a denser region of the galaxy where conditions were different. We can speculate, but we can't know for certain. What we can do is add this data to our growing understanding of galactic chemistry. One more point on the map of how elements are distributed through the Milky Way. This is what 3i Atlas offers us. Not answers exactly, but data, context, a reference point beyond our own experience. And in science, sometimes the most valuable discoveries are the ones that show us how much we still don't understand, that remind us how limited our perspective has been. For all of human history until 2017, our understanding of comets came from studying only the comets of our own solar system, billions of them perhaps, in the Oort cloud, at the outer edge of the sun's gravitational influence. But all of them formed here from the same original nebula, sharing a common chemistry and history. We were studying one sample, one experiment, one outcome of the planet formation process. Now, we have three. Just three, but three is infinitely more than one. Each interstellar visitor expands our sample size, gives us a new comparison, shows us what's universal and what's unique to our cosmic neighborhood. And the universe, it seems, is generous with these gifts when we're patient enough to watch for them. Scientists suggest that there might be dozens or hundreds of interstellar objects passing through the inner solar system at any given time, most too small or too dark to detect with current technology. They drift past us unseen, unnamed, unnoticed. Only the larger ones, or the ones that happen to pass, especially close, become visible enough for our surveys to spot them. The Atlas system that discovered this comet was designed to find asteroids that might pose a threat to Earth, scanning the sky repeatedly to spot anything moving against the background stars. It's a protective measure, a way of ensuring we see potential impacts coming far enough in advance to do something about them. But in watching for dangers, it also discovers wonders. It finds the visitors that pose no threat, that will never come close to our planet, but that carry information we desperately want to receive. 3i Atlas, for instance, will never threaten Earth. Its trajectory brings it nowhere near us. The closest it will come to our planet is about 170 million miles, nearly twice the distance from Earth to the Sun. Far, far away. Safe, untouchable, but observable. That's the gift. For a brief window of time, this ancient traveler is close enough, bright enough for our telescopes to see it clearly. Close enough for the Hubble Space Telescope to resolve its coma. Close enough for the James Webb Space Telescope to capture its infrared spectrum. Close enough for spacecraft throughout our solar system to turn their cameras and instruments toward it and gather data. And they have. Oh, they have. The response from the scientific community has been remarkable, coordinated, enthusiastic. More than 20 different space missions and observatories have been involved in studying 3i Atlas. From Earth-based telescopes to spacecraft at Mars, from instruments designed to study the sun to probes heading toward distant asteroids, all of them have contributed observations. It's not often that the universe hands us something so rare, so time-sensitive, so scientifically valuable. When it does, when a once-in-a-lifetime opportunity presents itself, the global community of astronomers and space agencies comes together in a way that's genuinely beautiful to witness. National boundaries don't matter. Individual missions share their data freely. Everyone contributes what they can, pooling resources and expertise to learn everything possible before the moment passes, because it will pass. That's the nature of interstellar visitors. They don't orbit, they don't return. They pass through our neighborhood once, and then they're gone, continuing their journey across the galaxy beyond our ability to see or follow. Right now, as you listen to these words, 3i Atlas is moving away from the sun, outbound, accelerating as it leaves the inner solar system behind. In the coming months, it will cross the orbit of Mars again, then Jupiter, then eventually leave behind even the most distant planets and enter the space between worlds where solar wind gives way to interstellar medium, and then silence, darkness. The long drift continues now, altered slightly by its encounter with our sun, carrying with it the faint warmth it absorbed during perihelion warmth that will slowly radiate away into the void until once again the comet is frozen solid, dormant a time, capsule sealed by temperature and time. Somewhere billions of years from now, it might pass near another star. Perhaps that star will have planets. Perhaps one of those planets will have life, will have creatures capable of looking up and wondering, of building telescopes and detecting the faint visitor passing through their sky. Perhaps they'll see it and wonder where it came from just as we do now. Or perhaps not. Perhaps 3i Atlas will wander the galaxy for eternity, never again, coming close enough to any star to be warmed, to be seen, to be wondered about. Just one small object among countless trillions drifting silently through the dark, carrying within its ice the frozen memory of a solar system that existed and then was gone. There's something profound in that possibility, something that touches on the temporary nature of all things, even on cosmic scales. Stars are born, stars die. Planets form and are eventually destroyed. Solar systems emerge from clouds of gas and then, given enough time, disperse again. Everything in the universe is in motion. Everything is changing. Nothing lasts forever. Except perhaps small things like 3i Atlas, too small to collapse under their own gravity and fuse atoms into new elements, too cold to undergo chemical reactions. Just ice and rock preserved by the vacuum of space and the frigid temperatures far from any star. In a sense, these small wanderers are the closest thing the universe has to permanent memories, physical records that persist long after the events that formed them have faded from possibility. And for a few months, one of those memories passed close enough to us that we could read a little of what it remembers. We could see the chemical signature of the molecular cloud from which it condensed. We could measure the effects of billions of years of cosmic ray exposure on its surface. We could watch it respond to our sun's warmth in ways both familiar and strange. What a gift that is. What an incredible privilege to live in a time when our technology is sophisticated enough to detect these visitors, our understanding deep enough to interpret what we see, our curiosity, strong enough to care about a small, icy body that poses no threat and offers no resources, that is simply interesting, simply beautiful, simply worth our attention because it's there and it's rare and it came from far away. This is what the next portions of our journey together will explore: the chemistry written in ice, the unprecedented global effort to observe and study 3i Atlas, the drama of its closest approach to the sun, hidden from Earth, but visible to spacecraft stationed elsewhere in the solar system, the questions it raises, some scientific, some philosophical, some that blur the line between wonder and understanding. But we're only beginning. We've established where this story starts with a discovery, a recognition that something extraordinary has entered our awareness. A visitor from forever, from the deep time between the stars, from a place and age we can only imagine. The journey continues, the mystery deepens, the data accumulates. Picture a moment when everything changes, when numbers on a screen tell you something that shouldn't be possible, something that rewrites what you thought you knew about the universe around you. July 1st, 2025. A telescope in Chile's Atacama Desert captures light that has traveled billions of years to reach us. And in those photons, astronomers find a truth that makes them hold their breath. We are not alone in watching the stars. The stars are watching us back, sending messengers we're only now learning to recognize. The Atlas Telescope Asteroid Terrestrial Impact Last Alert System sits high in the Chilean Andes at Rio Hurtado, where the sky is so dark and clear that stars seem close enough to touch. It's one of 4 Atlas units stationed around the globe, constantly scanning the heavens for anything that moves, anything that changes, anything that threatens. These robotic eyes were built to protect us, to spot asteroids that might one day cross Earth's path with enough warning to mount a defense. But on that first night of July, Atlas found something else entirely. Something that posed no threat, but demanded attention all the same. The detection system works through repetition and patience. Atlas photographs the same patch of sky multiple times each night, then compares the images. Most things stay fixed: the distant stars, the galaxies, the cosmic background. But some things move. Asteroids shift position hour by hour as they orbit the sun. Satellites streak past in minutes, and very rarely something appears that doesn't fit any known pattern. That's what happened with 3I Atlas. A faint point of light magnitude 19, far too dim for human eyes, visible only through long exposures and careful processing, appeared in images taken of a region between the constellations. When astronomers compared its position across multiple images, they saw movement, not unusual by itself. But when they plotted that movement, when they calculated the trajectory, the numbers didn't make sense. At first. You see, everything in our solar system follows rules. Kepler's laws, Newton's mathematics, Einstein's refinements. We understand orbital mechanics exquisitely well. Give us an object's position and velocity, and we can predict where it will be centuries from now, or where it was centuries ago. Objects bound by the sun's gravity trace, ellipses, closed loops that bring them around and around in eternal return. But 3I Atlas wasn't following a closed path. The orbit calculations kept producing what's called an eccentricity greater than 1. In orbital mechanics, eccentricity measures how stretched an orbit is. A perfect circle has eccentricity 0. Earth's slightly oval orbit has eccentricity 0.07. A very elongated ellipse like that of a long-period comet might have eccentricity 0.995, but 3I Atlas initial calculations suggested eccentricity somewhere around 1.035, greater than 1. And that means something profound. The trajectory isn't a closed ellipse at all, but a hyperbola, an open curve that comes in from infinity and returns to infinity, passing by the sun once and never circling back. Imagine standing on a hilltop and throwing a ball. No matter how hard you throw it, the ball follows a parabolic arc and falls back to Earth. You're bound by gravity. But if you could somehow throw that ball faster than escape velocity, roughly 25,000 miles per hour from Earth's surface, it would follow an open trajectory, leaving Earth behind, forever never to return. That's what 3I Atlas is doing with our entire solar system. The astronomers who first spotted this knew what it might mean, but they had to be certain. So, they reported their observations to the Minor Planet Center, the international clearinghouse for all asteroid and comet discoveries. Within hours, other observatories around the world were turning their instruments toward the same region of sky, gathering more data, refining the calculations. And with each new observation, the conclusion became unavoidable. This object was not gravitationally bound to our sun. It was moving too fast on the wrong kind of path. It had come from interstellar space, and it would return there. Only twice before in human history had this happened. The first time was October 19, 2017, when a telescope in Hawaii detected an object that would be named Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. That discovery stunned the astronomical community. For decades, theorists had predicted that interstellar objects must occasionally pass through our solar system, but detecting them had seemed nearly impossible. They would be faint, fast, rare, and yet there it was, tumbling through space on a hyperbolic trajectory, its origin unknown, its composition mysterious. Oumuamua changed everything. It proved that interstellar visitors were real, detectable, worth watching for. But it also frustrated us. By the time we realized what it was, Oumuamua was already too faint for detailed study. We managed to capture some data enough to determine it was oddly elongated, possibly tumbling rapidly, showing slight but measurable acceleration that might be outgassing or might be something else. But mostly we watched it disappear, knowing we'd missed our chance to truly understand it. Then came 2I Borisov, discovered on August 30th, 2019 by amateur astronomer Gennady Borisov using a telescope he built himself in Crimea. This one thankfully was spotted much earlier in its passage through our system, giving astronomers months to study it in detail. And Borisov was clearly a comet, actively outgassing, sporting a classic coma, and tail behaving exactly like the icy bodies we know from our own solar system. It even looks similar chemically with water ice and carbon monoxide, though with interesting differences in ratios that hinted at a colder formation environment than our comets typically experience. Borisov was a gift. It showed us that interstellar comets could be detected and studied, that they weren't impossibly rare or frustratingly brief. It gave us our first detailed look at material from another stellar system, our first chance to compare another solar system's chemistry with our own. And now, 3I Atlas, the third confirmed interstellar visitor. Detected earlier than Borisov, at a greater distance, giving us even more time to prepare observations and coordinate our global response. But here's what makes the discovery of 3I Atlas particularly remarkable. We almost missed it anyway. Not because of technological limitations, but because of timing and geometry. When 3I Atlas entered the inner solar system, the region inside Jupiter's orbit where sunlight is strong enough to begin heating comets, it was approaching from a direction nearly aligned with the plane of our solar system, the ecliptic. Most asteroids and comets stay close to this plane because they formed from the same flattened disk of material that birthed the planets. But interstellar objects can come from any direction unconstrained by our solar system's architecture. If 3I Atlas had approached from high above or below the ecliptic, from the galactic north or south, it might have been spotted much earlier, standing out against the background. But coming in nearly aligned with the ecliptic meant it spent months moving through the same regions where thousands of asteroids and comets already reside. It could easily have been mistaken for just another local object, if not for careful orbit calculations. This is one of the central challenges of detecting interstellar visitors, recognizing them as different. Our solar system contains billions of small bodies. The asteroid belt alone hosts millions. The Kuiper belt beyond Neptune contains countless icy objects. And the Oort cloud, that vast sphere of comets surrounding the Sun, at distances up to a light year away, probably contains trillions of individual bodies. Against that crowded background, spotting one interloper from another star system is like finding a single stranger in a city of millions possible, but only if you know what to look for. And what we look for ultimately is motion, trajectory, velocity. The mathematics of gravity tell us what belongs and what doesn't, what's on an elliptical orbit and what's on a hyperbolic escape trajectory. The scientists analyzing 3I Atlas's orbit had to account for numerous factors. The gravitational pull of the Sun, obviously, but also Jupiter, whose massive bulk can significantly alter the paths of comets that pass near it, and Mars and Saturn and even Earth to smaller degrees. They had to consider the pressure of sunlight, which exerts a tiny but measurable force on small objects. They had to account for outgassing from the comet itself, which creates thrust like a natural rocket engine, slightly altering the trajectory. All of these factors had to be included in the calculations to determine the comet's true path, and critically, its origin. And what those calculations revealed was stunning. 3I Atlas had approached our solar system with what's called an incoming asymptotic velocity, the speed it had relative to the Sun before gravity started accelerating it inward of about 22 kilometers per second. That's roughly 49,000 miles per hour, the speed the comet possessed, while drifting through interstellar space far from any star's influence. That velocity tells us something important. It's too fast to be explained by our sun's motion alone. Our sun orbits the galactic center at about 220 kilometers per second, carrying the entire solar system with it. Objects that form around the sun share that motion, moving with us as we journey around the galaxy. But 3I Atlas was moving at a different speed in a different direction, suggesting it had originated from a stellar system with a different orbital velocity around the galactic core. By analyzing that velocity difference, astronomers can make educated guesses about where 3I Atlas came from. Not a specific star, the uncertainties are too large for that, but a general region of the galaxy, a volume of space that might contain hundreds or thousands of stellar systems. Research suggests the comet likely originated within a few dozen light years of our current position, from a star that formed billions of years ago and may or may not still exist today. This is the detective work that makes interstellar discoveries so fascinating. We have a visitor, but we'll never know its precise home address. We have a traveler, but we can't reconstruct its complete itinerary. The galaxy is too large, time has been too long, the gravitational landscape too complex. What we have instead are clues, statistical likelihoods, ranges of possibility. And yet, those clues are enough to tell us something profound. The galaxy is full of these wanderers. Every stellar system probably produces them, objects ejected during the chaotic process of planet formation, or scattered into interstellar space by close encounters with passing stars. Over billions of years, the Milky Way becomes filled with this debris, small bodies drifting between the stars, occasionally passing through other solar systems purely by chance. Scientists estimate that at any given moment, there might be dozens or even hundreds of interstellar objects passing through the inner solar system, the region inside Jupiter's orbit, where sunlight is strong enough for us to see them. Most would be too small or too dark to detect with current technology. We see only the tip of the iceberg, the larger objects that happen to come close enough and are active enough to glow in our telescopes. Before 2017, we had never confirmed even one. Now we have 3. And each discovery refines our understanding of how common these visitors really are, how often we can expect to see them, how large our telescope surveys need to be to catch them reliably. The discovery of 3I Atlas then represents more than just one comet. It represents the maturation of our capability to watch the skies systematically, to process vast amounts of data, quickly to recognize the unusual among the ordinary. It represents the global network of astronomers and automated surveys that now monitor the heavens, continuously sharing data, in real time coordinating observations across continents. Atlas itself is part of that network. The system consists of 4 telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa, covering both hemispheres, scanning the entire visible sky multiple times each night. When one telescope spots something interesting, the others can immediately follow up, providing different viewing angles, tracking objects as they move across the sky. But Atlas doesn't work alone. As soon as the Minor Planet Center distributed the alert about a possible interstellar object, other facilities joined the effort. The Pan-STARRS survey in Hawaii, which had discovered Oumuamua, turned its attention to the new target. The Gemini Observatory, with its twin 8-meter telescopes in Hawaii and Chile, began taking spectra. Ground-based telescopes around the world added their observations, each contributing data that helped refine the orbit and characterize the object. And beyond Earth, in the darkness of space, more eyes were watching. The Hubble Space Telescope orbiting above our atmosphere, where the view is crystal clear, scheduled observations. The James Webb Space Telescope, the most powerful infrared observatory ever built, added 3I Atlas to its target list. Spacecraft throughout the solar system at Mars, heading toward Jupiter, studying the sun, all turned their instruments toward this unexpected visitor. This is how science works at its best. A discovery is made and the community responds. Data is shared freely. Expertise is pooled. Everyone contributes what they can, building a collective understanding that's greater than what any single observatory or researcher could achieve alone. Think about what this means. A telescope in Chile, designed to protect Earth from asteroid impacts, discovers an object that poses no threat whatsoever, but offers immense scientific value. Within hours, that discovery reaches scientists around the world. Within days, observatories on every continent are gathering data. Within weeks, space telescopes and interplanetary probes are contributing their unique perspectives. It's a level of global coordination that would have been impossible even a few decades ago. The technology, the communication networks, the willingness to collaborate across national and institutional boundaries, all of these things had to align for us to study 3I Atlas as thoroughly as we have. And yet, there's always a bittersweet quality to these discoveries. The moment we realize what we're seeing is also the moment we realize it's already leaving. Interstellar objects don't linger. They're not bound to our sun. They pass through in months, not years, and then they're gone forever. With 3I Atlas, we were fortunate. The discovery came early enough in its passage that we had months to prepare to coordinate to point our best instruments at it before it faded from view. But that time was finite, precious, unrepeatable. There's no going back to check something we missed. There's no second chance to run an experiment we didn't think of in time. Everything we learn about 3I Atlas, we must learn now during its brief transit through our neighborhood. Or we learn nothing at all. This urgency colors every aspect of studying interstellar visitors. Telescope time is fought over. Observation schedules are adjusted. Mission plans for spacecraft are modified on the fly to include this unexpected target. Because opportunities like this are measured in weeks and months, not years and decades. And every scientist involved knows they're witnessing something rare, something that might not happen again in their career or their lifetime. The third interstellar object ever confirmed, the first to be studied with the James Webb Space Telescope, the first to be observed by spacecraft at Mars during its passage. Each of these is a milestone, a first in the history of astronomy, but also hopefully not a last. As our surveys improve, as our telescopes grow more sensitive, as our automated detection systems become more sophisticated, we expect to find more of these visitors. Not every year, perhaps, but regularly enough that they become a routine part of astronomy rather than rare surprises. When that day comes, when detecting interstellar objects becomes commonplace, we'll look back at Oumuamua, at Borisov, at 3I Atlas as the pioneers. The first visitors we noticed, the first we studied, the ones that taught us how to recognize and characterize objects from beyond our solar system. But we're not there yet. You're still in the early days of interstellar astronomy, still learning the basics, still surprised each time something from the depths of space wanders past our sun. Each discovery is still precious, still urgent, still demanding our full attention before the moment passes and the visitor vanishes into the dark from which it came. And so, the global astronomical community mobilized. Telescopes watched, spacecraft maneuvered, data accumulated, and slowly observation by observation, spectrum by spectrum, a portrait of 3I Atlas began to emerge, not just where it came from and where it's going, but what it is, what it's made of, what secrets it carries. Close your eyes for a moment and imagine time not as seconds or minutes, but as eons. Imagine a journey so long that entire civilizations could rise and fall in the blink of an eye along its path. Imagine traveling through darkness, so complete, so vast, that the nearest star is just a distant point of light, no brighter than the faintest stars you see from Earth on a moonless night. This is the story written in ice and stone, carried across the galaxy by something smaller than a mountain, older than memory. Before 3I Atlas was a visitor passing through our solar system, before it was a discovery that made headlines, Before it was anything we could name or see, it was simply moving, falling, drifting through the void between stars for a span of time that defies human comprehension. How old is 3I Atlas? The question seems simple, but the answer opens doors to understanding we're only beginning to walk through. Scientists have approached this puzzle the same way they estimate the ages of stars, by looking at motion, at velocity, at the relationship between how fast something moves and how long it's been traveling. In our galaxy, there's a pattern. Older stars tend to have higher random velocities relative to the average motion of stars around the galactic center. It's a consequence of gravitational interactions over billions of years, each close pass by another star. Each transit through a spiral arm, each encounter with a giant molecular cloud, adds a little kick to a star's velocity, nudging it this way or that. Over time, these small perturbations accumulate, and the star's motion becomes less orderly, more random. Young stars freshly formed from collapsing gas clouds tend to move in neat circular orbits around the galaxy's center. But ancient stars, those born when the universe itself was young, have had billions of years to accumulate velocity kicks, and they move faster, more erratically, their paths less predictable. Researchers Astor Taylor from the University of Michigan and Darrell Seligman from Michigan State University applied this same principle to 3I Atlas. They looked at the comet's excess velocity, the difference between how fast it's moving and how fast an object born near the sun would typically move, and calculated what astronomers call a kinematic age. The number they arrived at, somewhere between 3 and 11 billion years old. Let that settle for a moment. 3 billion years ago, Earth was an alien world. The atmosphere contained almost no oxygen. The continents were arranged in configurations we wouldn't recognize. The only life was microbial single-celled organisms dwelling in oceans, or perhaps forming mats along ancient shorelines. Complex life plants, animals, anything visible to the naked eye wouldn't emerge for another 2 billion years. And 3I Atlas was already old, then already wandering the galaxy, already ancient. If we take the upper end of that estimate 11 billion years, we're talking about a time when the universe itself was less than 3 billion years old. The very first generation of stars, massive giants that lived fast and died young in spectacular supernovae, had already come and gone, seeding the cosmos with heavy elements. The second generation of stars, smaller and longer lived, were forming from that enriched material. Our sun wouldn't exist for another 7 billion years, Earth even longer. Try to visualize that span of time. 11 billion years. If you compress the entire history of the universe into a single year, with the Big Bang happening on January 1st at midnight, 3I Atlas would have formed around February 2nd. Our sun wouldn't ignite until late August. Earth wouldn't form until early September. And all of human civilization, from the first stone tools to the spacecraft we've sent beyond the planets, would occur in the final seconds before midnight on December 31st. For all of that time, 3I Atlas has been falling. Not falling toward anything exactly, but moving through the galaxy's gravitational landscape, following the curvature of space-time, created by billions of stars and vast clouds of dark matter. Its path curves, bends, responds to every massive object it passes, but never closes into an orbit. It drifts a piece of cosmic flotsam from a stellar system that may no longer exist. Scientists suggest that the comet's orbital period around the galactic center, the time it takes to complete one full circuit around the Milky Way's core, is approximately 250 million years. That's roughly the same as our sun's galactic year, the time it takes our entire solar system to trace one lap around the galaxy. But here's what makes that number astonishing. In the time 3I Atlas has existed, it has completed somewhere between 12 and 44 complete orbits around the galaxy. 12 times at minimum, it has circumnavigated the entire Milky Way. 44 times, possibly it has passed through the spiral arms, crossed the galactic plane, journeyed through regions of space we can barely observe. Each orbit would have been different. The galaxy itself is dynamic, constantly changing. Spiral arms rotate, but not at the same rate as individual stars. Gas clouds collapse into star clusters, then disperse. Stellar nurseries ignite with the blue-white brilliance of massive young stars, then fade as those stars exhaust their fuel and explode. The galactic ecosystem is in constant flux, reshaping itself over millions and billions of years. And through all of that, Change 3i Atlas traveled. Sometimes it might have passed through regions rich with gas and dust, picking up a coating of new material on its surface. Other times it journeyed through voids, empty reaches between the spiral arms, where matter is sparse and starlight dim. It felt the tidal forces of giant molecular clouds, the gravitational pull of globular clusters, the distant influence of the supermassive black hole at the galaxy's heart. But mostly it experienced nothing. Silence. Darkness. The space between stars is emptier than any vacuum we can create on Earth. In interstellar space, you might find one atom per cubic centimeter, sometimes fewer. For comparison, the air you're breathing right now contains about 30 billion atoms per cubic centimeter. In that profound emptiness, 3i Atlas was alone. No sunlight warmed its surface. No planetary companions orbited nearby. No asteroid belt neighbors disturbed its solitude. Just the faint glow of distant stars and the cosmic microwave background radiation, the afterglow of the Big Bang itself, providing a temperature barely above absolute zero. At those temperatures, roughly minus 270 degrees Celsius, just 3 degrees above the coldest possible temperature, chemical reactions essentially stop. Molecules don't interact. Ice doesn't sublimate. Everything freezes into a state of suspended animation. 3i's Atlas, for billions of years, was essentially a time capsule preserving in frozen form the chemical composition it had when it left its home system. This is one of the most valuable aspects of interstellar objects. They're not just visitors from other star systems, they're messengers from the past, carrying pristine samples of the molecular clouds that existed billions of years ago. When we analyze the chemistry of 3i Atlas, we're not just learning about another solar system. We're learning about the galaxy's chemical evolution, about how the mixture of elements has changed over cosmic time. The galaxy wasn't always like it is now. When the universe was young, it contained almost exclusively hydrogen and helium, the elements forged in the Big Bang itself. Every other element from carbon to iron to uranium had to be created inside stars through nuclear fusion in stellar cores, or in the violent explosions of supernovae. Over billions of years, as generations of stars lived and died, they gradually enriched the galaxy with heavy elements. Each supernova dispersed iron, silicon, oxygen, and dozens of other elements into the surrounding space. Each planetary nebula, the gentle death of a sun-like star, contributed carbon, nitrogen, oxygen. Slowly, the galaxy's chemical composition evolved, becoming more metal-rich, as astronomers say, where metal means anything heavier than helium. If 3i Atlas is truly 11 billion years old, it formed from a molecular cloud that existed when the galaxy was much less enriched than it is today. The ratios of elements in that ancient cloud would have been different from the ratios in the cloud that formed our solar system 4.6 billion years ago. And those ancient ratios are still preserved in the ice of 3i Atlas, frozen for eons, waiting for us to read them. But the journey itself, the long drift through interstellar space, also leaves marks. Cosmic rays, high-energy particles accelerated by supernova shock waves, and other violent events constantly bombard objects in space. Over billions of years, this radiation damages the surface layers of ice and rock, breaking apart molecules, creating new compounds, altering the chemistry in measurable ways. The longer an object has been exposed to cosmic rays, the more damage accumulates. By measuring certain isotopes created by cosmic ray interactions, scientists can estimate how long a surface has been exposed to space. It's similar to carbon dating, but using different nuclear reactions and working on much longer timescales. Early measurements of 3I Atlas's surface suggest significant cosmic ray exposure consistent with billions of years in interstellar space. The ice isn't pristine. It's been modified, processed, weathered by radiation. But beneath that altered surface layer in the comet's interior, the original chemistry might still be preserved, protected by the outer layers from the worst of the radiation damage. This creates a kind of archaeological stratigraphy in comets. The surface tells you about the journey, the interior tells you about the origin. And by studying both, by understanding how the layers differ, you can reconstruct not just where the comet came from, but what it experienced along the way. Think about what this means. We can't travel to other star systems. Even our fastest spacecraft, even the Voyager probes that are now leaving our solar system behind, are moving so slowly relative to interstellar distances that they won't reach another star for tens of thousands of years. We're trapped for now and for the foreseeable future in our small corner of the galaxy. But the galaxy isn't trapped. It sends us samples. Objects like 3I Atlas, ejected from other stellar systems drifting through the void, occasionally passing close enough to our sun for us to study them. They're natural space probes launched billions of years ago, arriving in our era, purely by chance, offering us a way to sample the chemistry and physics of distant star systems without ever leaving home. How did 3I Atlas begin its interstellar journey? We can't know for certain, but we can make educated guesses based on our understanding of how planetary systems form and evolve. Most likely it formed in the outer reaches of another solar system in the region, where temperatures were cold enough for water and other volatiles to condense into ice. This is where comets typically form far from their star, where rocky material mixed with frozen gases to create the dirty snowballs we recognize as comets. But the early solar system, any solar system, is a chaotic place. Young planets migrate inward or outward, their orbits shifting as they interact gravitationally with the disk of gas and dust from which they formed. Giant planets like Jupiter can scatter smaller objects, violently flinging some into the inner system, to become short-period comets, ejecting others entirely from the system. Research shows that this ejection process is common, perhaps inevitable. Computer simulations of planetary system formation suggest that for every planet that remains in stable orbit, hundreds or thousands of smaller bodies are ejected into interstellar space. It's the cost of creating a stable planetary system. The debris must go somewhere, and often it goes outward accelerated to escape velocity by gravitational slingshots around giant planets. So 3I Atlas was probably a casualty of planetary formation, a small body that happened to pass close to a massive planet at just the right angle, just the right velocity to be flung outward fast enough to escape its star's gravity entirely. Imagine that moment, a close encounter perhaps lasting only hours or days that determined the comet's fate for the next billions of years. One trajectory among infinite possibilities, one that happened to lead not to a stable orbit, not to a collision with a planet or a long elliptical path around the star, but to ejection, to exile, to an eternity of wandering. The planet that ejected it, assuming that's what happened, probably still exists. It might be a gas giant like Jupiter, or an ice giant like Neptune, or something in between. It's still orbiting its star, still dominating the gravitational landscape of its region, still occasionally flinging smaller bodies into interstellar space. It has no memory of 3I Atlas, no record of that long-ago encounter. Planets don't remember. They just follow the mathematics of gravity interaction after interaction forever. But 3I Atlas remembers, in a sense. Its trajectory remembers. The velocity it carries, the direction of its motion, the chemical composition frozen in its ice. All of these things encode information about that distant home system. about the star it once orbited, about the environment in which it formed. And now, that trajectory, that long fall through darkness, has brought it here, to us, to our solar system, to this brief moment when two paths intersect: the comet's ancient journey and our newly developed capability to recognize and study it. The probability of this happening is vanishingly small. The galaxy is vast. The solar system is tiny. The chances of any particular interstellar object passing close enough to our sun for us to detect it are measured in millions or billions to one against. And yet, it happened. It's happening right now. Some nights when you look up at the stars, does it ever strike you how unlikely it all is? That we exist at all on a planet that can support life? That we've developed the technology to see beyond our atmosphere, to send spacecraft to other worlds, to detect faint visitors from the depths of space? That we live in precisely the era when this particular ancient traveler happens to pass by? A few decades earlier, we wouldn't have had the telescopes to see it. A few decades later, it will be gone, returned to the darkness, continuing its journey to wherever gravity takes it next. We're witnessing something that has waited billions of years to be witnessed, and will wait billions more before anyone else, anywhere else, might notice it passing by. The journey of 3I Atlas, then, is not just a story about distance and time. It's a story about patience, about the slow unfolding of cosmic processes, about the way the universe occasionally arranges itself into moments of connection across vast divides. For billions of years, this small icy body has been falling through the galaxy, changing slowly, or not at all, accumulating cosmic ray damage and the subtle gravitational influences of passing stars. And then, in the late summer of 2025, it enters the sphere of attention of a species on a pale blue planet, a species that has just barely developed the capability to recognize it for what it is. We have months to study it, maybe a year or two before it fades beyond the reach of our telescopes, and then it will leave accelerating as it climbs back out of the sun's gravitational well, returning to the velocity it had when it arrived, continuing its orbit around the galaxy. 250 million years from now, give or take, it will complete another lap. The sun will have moved to a different location in its own galactic orbit. Earth will have changed in ways we can't predict. Humanity, if we still exist, might have spread to other stars, or might have vanished entirely. And 3I Atlas will pass through some other region of the galaxy, perhaps encountering some other planetary system, perhaps being noticed by some other civilization, with telescopes and curiosity. Or perhaps not. Perhaps it will continue its journey, unobserved, unmeasured, unnamed, for another few billion years, until finally it passes too close to a star or a black hole, and tidal forces tear it apart, or it collides with a planet or some other ending finds it. But for now, in this moment, it is here, and we are watching. And in its ice, in its trajectory, in every photon of reflected sunlight, we're reading the story of a journey that began before our world existed and will continue long after we're gone. The story deepens as we move closer, as we turn our finest instruments toward this traveler and begin to decode what it carries. What messages are written in molecules? Imagine holding a snowflake in your hand, not the delicate kind that melts on contact, but one frozen so deeply that no warmth could touch it. Now, imagine that snowflake is a mountain, and that mountain has been falling through absolute darkness for longer than complex life has existed on Earth. What would it look like when it finally catches sunlight again? What would its surface remember? The first images of 3I Atlas came from Hubble, that ancient eye still watching faithfully from orbit above our atmosphere. On July 21st, 2025, when the comet was still 277 million miles from Earth, Hubble's wide field camera captured something remarkable. Not just a point of light, but a shape, a structure, a teardrop cocoon glowing softly against the void. But here's the beautiful complexity: what Hubble saw wasn't the comet itself. Not exactly. It was the comet's breath, its exhalation, the cloud of gas and dust that forms when ice that has been frozen for billions of years suddenly remembers what warmth feels like. Scientists call this cloud the coma, from the Latin word for hair. Ancient astronomers looking up with naked eyes saw comets as stars with flowing hair streaming behind them, and the name has persisted through centuries. The coma is the atmosphere of a comet, but unlike Earth's atmosphere held close by gravity, a comet's coma escapes constantly blown away by solar wind and radiation's pressure streaming behind the nucleus in tails that can stretch for millions of miles. What causes this transformation? The answer lies in a process called sublimation, when a solid transforms directly into gas without passing through a liquid phase. Here on Earth, we see this happen with dry, ice-frozen carbon dioxide that turns directly into vapor at room temperature. But in spacewater, ice can sublimate too, if conditions are right. And for 3I Atlas approaching our sun after billions of years, in the deep freeze of interstellar space conditions, we're finally right. The surface of the comet, as it moved inside Jupiter's orbit and sunlight grew stronger, began to warm. Not much. We're still talking about temperatures far below freezing by Earth standards, but enough. Enough for the topmost layers of ice to transform molecule by molecule from solid to gas. Water molecules breaking free from the crystal lattice. Carbon dioxide escaping. Other volatiles, compounds of carbon, nitrogen, sulfur, all beginning to vaporize. And as these gases escape, they carry with them tiny particles of dust grains that were mixed with the ice when the comet formed billions of years ago. These dust particles reflect sunlight, making the coma visible, giving 3I Atlas its glow. Hubble's images revealed this process in exquisite detail. The teardrop shape isn't random, it's sculpted by forces. On the side facing the sun, heating is strongest sublimation, most vigorous, creating a plume of material jetting outward. But that material doesn't travel straight. It gets caught by solar wind, by radiation pressure, by the comet's own rotation, and curves backward, forming the characteristic tail that always points away from the sun, regardless of which direction the comet is traveling. Because the images were taken while tracking the comet's motion, the background stars appear as streaks-long exposures, capturing their apparent movement across the frame, while the comet remains centered. It's a reminder that everything we see is in motion, that the universe doesn't hold still for our convenience. We capture moments, frozen instants, knowing that by the time we process the data, reality has already moved on. But within those frozen moments lies information. The brightness of the coma tells us about the rate of gas production. The shape of the plume suggests which side of the nucleus is facing the sun, how the surface is responding to heating. The length and structure of the tail reveal the density of the solar wind, the strength of radiation pressure, the way plasma and dust separate into distinct streams. And beneath all of that visible activity hidden within the bright cloud lies the actual solid body, the nucleus of 3I Atlas, the real comet the ancient ice preserved from another stellar system. Measuring the size of a comet nucleus is surprisingly difficult when it's surrounded by a bright, obscuring coma. It's like trying to see a flashlight bulb when it's turned on and pointed at you. The glare overwhelms the object itself. Astronomers have to use careful techniques comparing the total brightness to models of how much light the coma should produce, subtracting that to estimate what's left, what must be coming from the solid surface beneath. Based on Hubble observations from August 20th, 2025, scientists estimated that the nucleus of 3I Atlas has a diameter somewhere between 440 meters and 5.6 kilometers. That's an enormous uncertainty range. The upper limit is more than 10 times larger than the lower limit. A kilometer-sized nucleus would be massive for an interstellar object, comparable to or larger than 2I Borisov. A 440-meter nucleus would be much smaller, more like a large asteroid. Why such uncertainty? Because measuring the coma's contribution to the total brightness is difficult. We don't know exactly how reflective the dust particles are, how much gas they're mixed with, how the distribution varies across the coma. We make our best estimates based on observations of other comets, but every comet is unique, and 3I Atlas coming from another stellar system entirely might not follow the same patterns. More recent analysis suggests the nucleus is probably on the smaller end of that range, perhaps less than a kilometer across. The rate at which the comet is losing mass, the amount of gas and dust streaming off its surface, seems too low for a very large nucleus. It's as if the comet is exhaling gently, rather than vigorously suggesting there isn't much surface area exposed to sunlight, which implies a smaller body. But even the lower estimate is substantial. 440 meters. That's taller than the Empire State Building, larger than most mountains you might climb in a weekend. An object that size, composed of ice and rock, would have a mass of hundreds of millions of tons. Not massive by planetary standards, but far from insignificant. And it's rotating. Almost certainly rotating, though. We haven't yet been able to measure the rotation period directly. All small bodies in space rotate, acquiring angular momentum from the collisions and gravitational interactions that form them. Some tumble chaotically, spinning around multiple axes. Others rotate more smoothly, turning like a wheel around a single axis. As 3I Atlas rotates, different parts of its surface face the sun in turn. Areas that enter sunlight begin to warm and sublimate. Areas rotating into shadow, cool, and the sublimation slows or stops. This creates jets of gas and dust that turn on and off, that vary in intensity and direction, as the nucleus spins, creating complex patterns in the coma that shift over hours and days. Italian astronomers analyzing the shape of the coma in Hubble images from August 2025 suggested that the rotational axes of 3I Atlas, the imaginary line through its center around which it spins, might be tilted in a particular direction relative to the comet's orbital plane. Their analysis indicated two possible orientations, though they couldn't determine which was correct without more data. It's detective work inferring the shape and orientation of an object you can't see directly by studying the shadows and patterns it creates in the material streaming away from it. The surface of the nucleus itself remains largely mysterious. We haven't resolved it directly. The comet is too far away, too small, too enshrouded in its own atmosphere for even Hubble to show us surface features. But we can make educated guesses based on what we know about other comets. Comet surfaces are dark, surprisingly dark. Darker than coal, darker than asphalt, reflecting only 3 to 5% of the sunlight that hits them. This darkness comes from organic compounds, complex molecules of carbon, hydrogen, oxygen, nitrogen, that form a terry crust on the surface residue left behind as ices sublimate and volatile materials escape. Think about what happens when you leave a frozen dinner out too long. The surface dries out, becomes discolored forms, a hardened layer, while the interior remains frozen. Comet surfaces do something similar, but over millions or billions of years. The topmost layers lose their volatiles to space, leaving behind a lag deposit of non-volatile material, dust, organics, rocky grains, that insulates the ice below and slows further sublimation. This creates a patchy, heterogeneous surface. Some areas might be covered by thick lag deposits that barely sublimate at all. Other areas might be fresher ice exposed by recent activity, or the collapse of a crust layer actively venting gas and dust. Crater-like pits might form where subsurface ice sublimates, creating cavities that eventually collapse, exposing fresh material. For 3I Atlas, we can add another layer of complexity: billions of years of cosmic ray exposure in interstellar space. High-energy particles constantly bombarding the surface, breaking apart molecules, creating new compounds, altering the chemistry in ways that don't happen to comets that have spent their entire existence within a solar system's protective bubble. This weathering process, called space weathering, darkens surfaces, creates a reddish coloration, and forms complex organic molecules that can only exist under the intense radiation conditions of deep space. The surface of 3I Atlas might look quite different from our solar system's comets, even if the interior composition is similar, simply because it's been exposed to a different environment for a longer time. But as the comet approaches the sun, as heating penetrates deeper into the nucleus layers beneath that ancient weathered crust begin to sublimate, fresh material breaks through. The original chemistry preserved in frozen form since the comet's formation starts to emerge. And that's where the story gets truly fascinating. Scientists have detected multiple compounds in 3I Atlas's coma, each one a clue to the conditions that existed in the molecular cloud that formed the comet billions of years ago. Water ice was confirmed first on July 20th, 2025, based on near-infrared spectroscopic observations from the Gemini South Telescope and NASA's Infrared Telescope facility. The signature was unmistakable absorption features at specific wavelengths that could only be water in frozen form, sublimating from the nucleus and reflecting sunlight before dispersing into space. Water. The same molecule that fills Earth's oceans, that makes up most of your body, that's essential to all life as we know it. And here it is, again frozen in a comet from another star system, confirming that water is truly universal, that the chemistry which allows life to exist here operates the same way everywhere in the galaxy. But water wasn't alone. Observations by NASA's Swift Observatory in late July and early August detected hydroxyl ions, OH molecules, which are fragments of water, molecules broken apart by ultraviolet sunlight. And ultraviolet signatures of water, vapor itself, the gaseous form streaming away from the nucleus in the solar wind. Then came carbon dioxide. On August 21st, 2025, astronomers using NASA's SPHERE-X mission and working with Caltech reported detecting both water ice and carbon dioxide in mid-August observations. CO2 is common in solar system comets too, but the abundance relative to water seemed higher in 3I Atlas, a subtle difference that hints at formation conditions that were perhaps colder or occurred from gas with a different ratio of carbon to oxygen. And there were more exotic detections. On August 22nd, astronomers at Lowell Observatory reported the first tentative detection of cyanide emission, CN molecules, compounds of carbon and nitrogen that form when more complex molecules break apart in sunlight. Cyanide sounds ominous, toxic, deadly. But in comets, it's just another molecule, one of many carbon-nitrogen compounds that were present in the original molecular cloud. Spectroscopic observations by the Very Large Telescope on August 21st confirmed the cyanide detection and found something else: nickel. Metallic nickel somehow present in the gas, streaming off the comet's surface, glowing at specific wavelengths as it interacted with ultraviolet light. Nickel in comets isn't unprecedented. It's been detected in solar system comets before, but it's surprising. Nickel is a refractory element, meaning it doesn't vaporize easily. It shouldn't be present in significant amounts in the coma of a comet unless the nucleus contains metallic grains, or the surface is hot enough to vaporize rock itself. Its presence suggests something about the comet's composition, about the mix of ice and dust, about the tiny metal-rich particles that were incorporated into the ice when the comet formed. Interestingly, iron-nickel's close chemical cousin, usually found alongside it in meteorites and rocky bodies, seemed to be present in lower abundance than expected. Observations didn't show strong iron emission lines, suggesting that whatever process incorporated nickel into 3I Atlas didn't incorporate iron in the same proportion. Another subtle difference, another clue that the chemistry of the molecular cloud that formed this comet was not quite the same as the cloud that formed our solar system. Each of these detections required different techniques, different instruments, different wavelengths of observation. Water shows up best in the infrared, where the vibration and rotation of water molecules create distinctive absorption patterns. Cyanide glows in the ultraviolet and visible spectrum. Nickel reveals itself through very specific emission lines that require high-resolution spectrographs to detect. Taken together, these observations paint a chemical portrait of 3I Atlas, a body composed primarily of water ice like most comets, but with elevated carbon dioxide, detectable nickel, noticeable cyanide precursors, and a suite of organic compounds we are only beginning to inventory. Similar to our comets in general composition, but different in details and ratios, in the subtle fingerprints that reveal where and when it formed. This is what we mean when we say 3I Atlas is a messenger. It's not just telling us it came from somewhere else, it's telling us what the somewhere else was like. The chemistry of its ice reflects the chemistry of its birth cloud. The ratios of elements mirror the ratios that existed in that region of the galaxy billions of years ago. By measuring these ancient frozen samples, we're sampling a part of the galaxy we'll never visit, learning about stellar systems that might not even exist anymore. And the coma itself, the bright cloud that makes the comet visible, is more than just a pretty glow. It's a laboratory, a place where chemical reactions are happening in real time, under conditions we can observe and measure. As ice sublimates, as molecules are broken apart by sunlight, as dust grains collide and interact with plasma. In the solar wind, we're watching chemistry unfold in an environment very different from anything on Earth. The dust in the coma, for instance, isn't uniform. It's a mixture of particle sizes from tiny submicron grains, smaller than bacteria, to larger chunks the size of sand grains or pebbles. Each size behaves differently in sunlight. Small particles are pushed away by radiation pressure, while larger ones are less affected and fall back toward the nucleus or drift away more slowly. This creates a sorting effect, a gradient in particle size across the coma, which we can detect by analyzing how the coma's brightness changes at different wavelengths. And the shape of the coma evolves as the comet moves. Closer to the sun, heating intensifies, sublimation accelerates. The coma grows brighter and more extended. Farther from the sun, activity slows the coma, dims and contracts. We're watching a dynamic system respond to changing conditions, and in that response, we can read information about the comet's interior, how deeply the heat penetrates, how quickly ice can sublimate, whether there are layers of different composition beneath the surface. Some researchers have noted that the brightness variations of 3I Atlas changed over time. In July 2025, the comet showed brightness fluctuations of about 0.3 magnitudes, a 30% variation, in brightness likely caused by rotation, bringing different surface features into view. But by late July, those variations had decreased to about 0, 2 magnitudes suggesting that the nucleus was becoming more uniformly active, that sublimation was spreading across the surface as heating increased, smoothing out the brightness variations caused by patchy activity. It's as though the comet was waking up gradually, going from a state where only certain areas were active, to a state where the entire sunlit hemisphere was contributing to the coma. A transformation from sleep to wakefulness, driven by the patient, persistent warmth of our sun. And through all of this observation, all of this measurement and analysis, we're confronting a humbling truth. Even with our best instruments, we're still seeing only the surface of the mystery. The nucleus itself remains hidden. The interior chemistry, the structure to the detailed composition, all of it is inferred, estimated, guessed at, based on what we can observe from the outside. We wanted to send a spacecraft to 3I Atlas to intercept it and study it up close. In July 2025, a team led by researcher Atsuhiro Yaginuma published a study examining the feasibility of launching a mission to rendezvous with the comet. Their conclusion was disappointing, but unsurprising. Any spacecraft launched after the comet's discovery would require a delta V, a change in velocity of at least 24 kilometers per second, far beyond the capability of any propulsion system we currently possess. By the time we detected 3I Atlas, it was already too late to catch it. The comet was moving too fast on a trajectory that didn't align with any mission profile we could achieve. We could have launched spacecraft if we'd had years of warning, if we'd detected the comet farther out while it was still approaching. But with only months between discovery and perihelion, we were limited to remote observation. It's a frustration that every astronomer studying interstellar objects feels. We want to touch these visitors, to land on them, to drill into their ice and analyze it directly. But they move through our neighborhood so quickly, and we detect them so late that all we can do is watch them pass. We're spectators to a cosmic parade, unable to join, only observe. And yet observation yields understanding. Each spectrum we capture, each image we process, each data point we add to our models, all of it brings us closer to truly knowing this visitor, to understanding what it is and what it represents. The shape of a stranger, revealed slowly through patience and persistence, through the accumulated efforts of hundreds of astronomers and dozens of instruments, through the careful application of physics and chemistry to decode messages written in light. The story continues to unfold. The chemistry deepens, the codes hidden in molecules wait to be fully deciphered. Every atom tells a story. Every molecule is a memory, frozen in time, waiting to be read. When you look at ice from another star system, ice that condensed from gases that swirled around a sun that may no longer shine, you're not just seeing water. You're seeing a library written in elements, an archive of conditions that existed when galaxies were younger, and stars were arranging themselves into patterns we'll never witness. The chemistry of 3I Atlas is not just data. It's a conversation across billions of years, a message in a bottle thrown into the cosmic ocean by processes we're only beginning to understand. And in that message, encoded in the ratios of molecules and the abundance of elements, lies something precious, a comparison. A way to measure our own solar system against another, to see what's universal and what's unique to understand, if the chemistry that gave rise to life here is common or rare. Think about how we learn about distant places. Before satellites, before airplanes, before even telegraphs, people learned about far corners of the world through sample seeds brought back by travelers, minerals collected from distant mountains, water from foreign rivers. Each sample told a story about where it came from, what conditions existed there, what might grow or live in that environment. 3I Atlas is that kind of sample, but from an incomparably more distant place. A piece of another solar system delivered to us by chance and gravity, offering us direct physical evidence of chemistry that happened somewhere else, sometime else, under conditions we can only imagine. The first profound realization from studying 3I Atlas's chemistry was how familiar it seemed, and yet how subtly different. Water ice, yes, the same H2O that fills our oceans. Carbon dioxide, yes. CO2, the same compound we exhale with every breath. But the proportions, the ratios, the minor constituents, those told a different story. Scientists analyzing spectra from NASA's SPHERE-X mission and the California Institute of Technology found that 3I Atlas appears to have a higher ratio of carbon dioxide to water than is typical for comets in our solar system. Not dramatically higher, we're talking about differences of maybe 20 or 30%, but measurably different. Consistently different across multiple observations. Why would that matter? Because the ratio of CO2 to H2O in a comet depends on the temperature and pressure conditions in the disk of gas and dust where the comet formed. Water ice condenses at warmer temperatures than carbon dioxide ice. If you're forming in a slightly colder environment or from gas that has a slightly different composition, you'll incorporate relatively more CO2 into your ice. This suggests that the molecular cloud from which 3I Atlas formed, or at least the particular region of that cloud where this comet condensed, was either colder than the region where our solar system's comets formed, or had a higher abundance of carbon relative to oxygen. Both possibilities are interesting. Both tell us something about the diversity of stellar nurseries, about how conditions can vary even within a single galaxy. Our solar system formed from what's called the solar nebula, a cloud of gas and dust that collapsed under its own gravity about 4.6 billion years ago. That cloud had a particular chemical composition inherited from the stars that lived and died before our sun existed. Each supernova, each stellar wind, each previous generation of stars contributed elements to the interstellar medium, gradually enriching it with heavy elements. But not every molecular cloud is enriched equally. Some regions of the galaxy have undergone more stellar processing, more generations of star formation and death, and thus have higher metallicity, more elements heavier than hydrogen and helium. Other regions are more pristine, less processed, closer to the original composition of the universe after the Big Bang. If 3I Atlas formed in a region with slightly different metallicity than our solar system, we would expect to see exactly what we're observing, similar overall composition, but with ratios of elements shifted slightly one way or another. It's like comparing two recipes that use the same basic ingredients, but in different proportions. The result is recognizably similar, but noticeably distinct. The detection of nickel in 3I Atlas's coma was particularly intriguing. Nickel is what astronomers call a refractory element. It doesn't vaporize easily. Under typical comet conditions, nickel should remain locked in solid grains, not floating freely in the gas phase, where we can detect it spectroscopically. And yet, there it was glowing at characteristic wavelengths in observations by the Very Large Telescope in August 2025. The emission lines were clear, unmistakable. Nickel atoms somehow liberated from solid material, excited by ultraviolet sunlight emitting photons that traveled 200 million miles to be captured by telescopes on Earth. How does nickel end up in a comet's coma? Scientists suggest several possibilities. One is that the comet contains tiny metallic grains, microscopic fragments of iron-nickel metal, similar to what we find in meteorites. And these grains are small enough to be ejected, with the sublimating ice then vaporized by solar heating or UV radiation. Another possibility is that the surface of the nucleus becomes hot enough in direct sunlight to begin vaporizing not just ice, but also some of the rocky material, releasing metals directly from the surface. A third, more exotic possibility involves the original formation environment. In the disk around a young star, where planets and comets are forming, there are complex chemical reactions happening. Carbon monoxide can react with hydrogen to form complex organic molecules. Water can react with silicates to form hydrated minerals. And under certain conditions, metals can form carbonyl compounds molecules where metal atoms bond with carbon monoxide. Nickel carbonyl, for instance, is volatile at relatively low temperatures. If such compounds formed in the disk around 3I Atlas's parent star, they could be incorporated into the comet's ice, then released when that ice sublimes, explaining the presence of gaseous nickel in the coma, without requiring extremely high temperatures. Each of these scenarios has implications. Each tells us something different about conditions in that ancient stellar system. The presence of metallic grains would suggest that the disk had undergone some melting and differentiation, that high-temperature processing had occurred. Surface vaporization of rock would require intense solar heating. And nickel carbonyl would imply particular chemical conditions, a reducing environment rich in carbon monoxide. We don't yet know which explanation is correct, or if the answer is some combination of all three. But the question itself is valuable because it makes us think carefully about comet formation, about the diversity of processes that can occur in planetary systems, about the many paths that can lead to the same end result, an icy body drifting through space. The detection of cyanide CN molecules in the coma is another piece of the chemical puzzle. Cyanide in comets comes from the breakdown of larger molecules, probably hydrogen cyanide, HCN, or cyanide-bearing, organic compounds frozen in the nucleus. When these molecules are released into sunlight, ultraviolet radiation breaks them apart, creating the CN fragments we observe. Hydrogen cyanide is one of the fundamental building blocks of complex organic chemistry. In the presence of water and energy, HCN can polymerize link together into longer chains, forming the precursors of amino acids and nucleotide bases, the molecules essential for life as we know it. The detection of cyanide in 3I Atlas, then, isn't just cataloging another molecule. It's confirming that the chemistry necessary for life is present even in bodies formed around other stars. This is one of the deepest questions that interstellar objects help us address. Is the chemistry of life universal? Do all stellar systems produce the same kinds of organic molecules? Or is there something special, something rare about the particular mix of elements and conditions that led to life on Earth? So far, every interstellar object we've studied in detail has shown chemistry that's broadly compatible with life. Water-carbon compounds, nitrogen-bearing molecules, all the ingredients are there. Not life itself, of course, but the raw materials, the chemical building blocks from which life could potentially emerge if conditions were right. It's reassuring in a way. It suggests that we're not chemically isolated, that the processes which led to life here are operating throughout the galaxy. Wherever stars form, wherever planetary systems coalesce from disks of gas and dust, the same elements are being incorporated, the same molecules are being synthesized, the same potential exists. But there are limits to what chemistry alone can tell us. Knowing that a comet contains water and organic molecules doesn't tell us whether planets formed in that system. It doesn't tell us whether any of those planets were habitable. It certainly doesn't tell us whether life actually arose. What it does tell us is that the universe is chemically fertile, that the ingredients for life are common, that wherever we eventually go, if we eventually go, we're likely to find familiar chemistry, even if the specific ratios and abundances differ from what we know here. The study of 3I Atlas's chemistry has also revealed what's missing or present in lower abundance than expected. Iron, for instance, nickel's close companion in most cosmic contexts, seems to be underrepresented. Observations didn't show strong iron emission lines, suggesting that whatever process incorporated nickel into the comet's composition was selective, favoring nickel over iron in a way that's unusual. This is actually quite puzzling. In meteorites, in asteroids, in the sun itself, iron and nickel are typically found in relatively fixed proportions, reflecting the way they're produced by nuclear fusion in stellar cores and dispersed by supernovae. To find nickel without proportional iron suggests either unusual chemistry during the comet's formation, or some process that separated the elements after formation, or perhaps measurement biases we don't fully understand. Science thrives on such puzzles. When observations don't match expectations, when something seems anomalous or unusual, that's when we learn the most. It forces us to reconsider our assumptions, to look more carefully at our models, to ask whether we really understand the processes we thought we did. The abundance of carbon dioxide relative to water in 3I Atlas, the presence of nickel, the detection of various organic molecules, each of these is a piece of evidence about the molecular cloud from which the comet formed. And by collecting enough pieces, by studying enough interstellar objects, we can start to map the chemical diversity of the galaxy itself. Imagine building a library of interstellar chemistry. Each visitor that passes through our solar system adds a new volume, a new data point. Over time, patterns would emerge. We'd see which elements and molecules are truly universal, present in the same ratios everywhere, and we'd see which vary, which depend on local conditions, which tell us about the history and evolution of different regions of the galaxy. Right now, with only 3 confirmed interstellar objects studied in detail, we're still in the early stages of building that library. Oumuamua gave us hints but frustrated us with its quick departure and unusual behavior. 2I Borisov showed us that interstellar comets can be remarkably similar to our own. And now, 3I Atlas is adding nuance, showing us that similarity doesn't mean identity, that subtle differences exist and matter. The chemical analysis of 3I Atlas has been made possible by instruments that didn't exist a generation ago. The James Webb Space Telescope, launched in late 2021, brought unprecedented infrared sensitivity to bear on the comet, capturing spectra that revealed molecules invisible to earlier observatories. Webb can see the fingerprints of complex organic compounds, the vibrational signatures of carbon-carbon bonds, the subtle features that tell us about molecular structure. The Very Large Telescope's high-resolution spectrographs could detect individual emission lines from atoms like nickel and iron, measuring them with enough precision to calculate abundances. Ground-based infrared telescopes like Gemini South and NASA's Infrared Telescope Facility captured the signatures of ices on the comet's surface, distinguishing between water ice, CO2 ice, and other frozen volatiles. Each instrument contributes its unique perspective, its particular strength. Together they create a multidimensional portrait of the comet's chemistry, not just a list of what's present, but information about temperatures, densities, physical states, how molecules are distributed spatially across the coma, how abundances change as the comet approaches the sun. This kind of comprehensive analysis would have been impossible even 10 years ago. The technology has evolved, the techniques have been refined, and most importantly, the global coordination necessary to point multiple world-class observatories at the same target at the right times has matured into a well-oiled system. And yet, for all we've learned, for all the molecules we've detected, and the ratios we've measured, we're still only scratching the surface. The interior of 3I Atlas remains a mystery. The chemistry we observe is from the outer layers, the material that's actively sublimating. Deeper inside, protected from solar heating and cosmic rays, there might be more pristine ice, more ancient molecules, chemistry that hasn't been altered since the comet's formation. We'll never know what that pristine interior contains. We can't drill into the comet, can't bring back samples for laboratory analysis. We're limited to remote observation, to measuring what the comet voluntarily releases as it's heated by our sun. But perhaps that's part of the beauty of studying interstellar objects. They remain mysterious, partially known, preserving some secrets. We learn what we can. We make our measurements, we build our models, and we accept that some questions will remain unanswered. Not forever. Maybe someday we'll have the technology to intercept an interstellar visitor early enough to send a spacecraft to rendezvous with it. But for now, we work with what we have. And what we have from 3I Atlas is already extraordinary. We have confirmed detection of water, carbon dioxide, carbon monoxide, cyanide compounds, nickel, and carbonyl sulfide in the coma. We have measurements of ratios, estimates of abundances, observations of how the chemistry changes as the comet moves through different regions of the solar system. We have spectra captured at multiple wavelengths from multiple instruments, a data set rich enough to keep scientists busy for years, analyzing and interpreting. Each molecule detected is a small victory, a confirmation that our instruments work, that our understanding of spectroscopy is sound, that we can extract meaningful information from faint signals that have traveled across interplanetary space. And each measurement contributes to a larger understanding, a growing picture of what comets from other stellar systems are like, how they compare to our own, what this tells us about the galaxy's chemical evolution. Have you ever wondered what it would be like to taste starlight? To sample directly the chemistry of distant places, to know through direct evidence rather than inference what other parts of the universe are made of. In a sense, that's what we're doing when we study interstellar objects. We're sampling distant stellar systems without leaving home, reading chemical signatures that tell us stories about places we'll never visit. There's something almost intimate about it. These molecules, water, carbon dioxide, simple organic compounds, are the same chemistry that surrounds us here on Earth. The same H2O that falls as rain that fills our cells, that makes life possible. The same CO2 that plants breathe, that cycles through our atmosphere, that we exhale with every breath. To find these molecules in an object from another star system confirms something profound: we are chemically connected to the rest of the galaxy. The elements that make up our bodies were forged in stars that exploded billions of years ago, and those same elements, following the same physical and chemical laws, assembled into similar compounds elsewhere, forming the ices and rocks and gases of other stellar systems. We are made of the same stuff as 3I Atlas. Different proportions, different histories, different journeys through space and time, but ultimately the same atoms, the same molecules, the same fundamental chemistry operating everywhere, connecting all matter in the universe through shared origin and shared physics. As the chemistry unfolds further, as more molecules are identified and measured, the portrait of this ancient traveler continues to sharpen detail by detail, spectrum by spectrum. Imagine standing in a city where every person suddenly stops what they're doing and turns to look at the same thing: a bird passing overhead, a cloud taking an unusual shape, something rare enough that everyone, for just a moment, shares the same focus. Now, expand that city to the size of the solar system, and instead of people imagine spacecraft and telescopes, each with their own mission, their own purpose, their own patch of sky to study. And yet, when something extraordinary passes through, they all turn, they all watch, they all contribute what they can to understanding this singular moment. This is what happened with 3I Atlas, a coordination of observation unprecedented in scope, a symphony of instruments playing together across distances that dwarf human comprehension. Over 20 missions and observatories scattered from Earth to Mars to Jupiter and beyond, all focusing their attention on one small icy visitor that would pass through our neighborhood just once, never to return. The hunt began the moment the discovery was confirmed. Within hours of Atlas reporting the detection on July the 1st, 2025, the astronomical community mobilized with a speed and efficiency that would have seemed impossible a generation ago. Emails circulated through research groups. Telescope time was requisitioned, observation schedules rearranged. Mission planners for spacecraft millions of miles from Earth began calculating whether their instruments could contribute, whether their trajectories would allow even a brief glimpse of this unexpected target. What emerged was something beautiful, a global, indeed solar system-wide collaboration, where competition dissolved in the face of shared curiosity. This wasn't about any single nation or institution claiming credit. This was about humanity collectively deciding that understanding this visitor mattered more than any individual agenda. Consider what had to happen for this coordination to work. NASA missions had to share data with ESA missions. Ground-based observatories in Hawaii had to coordinate with telescopes in Chile and South Africa. Spacecraft designed to study Mars had to be convinced to look away from their primary targets to spend precious observation time on a comet that would be visible for only days from their vantage point. And it worked. The response was remarkable, comprehensive, almost poetic in its scope. Hubble Space Telescope, that venerable eye that has been watching the universe since 1990, scheduled multiple observation sessions. Hubble orbits Earth every 96 minutes, giving it a unique vantage above our atmosphere, where no turbulence blurs the view, no weather interrupts observations. Its Wide-Field Camera 3 captured the first detailed images of 3I Atlas's coma, revealing structure and detail invisible from ground-based telescopes. Each Hubble observation required careful planning. The telescope had to be pointed precisely, tracking the comet's motion against the background stars. Exposure times had to be calculated to capture enough light without saturating the detectors. Multiple filters were used to observe at different wavelengths, building up a multispectral portrait of the comet's activity. The images Hubble returned showed not just a fuzzy blob, but structured the teardrop shape of the coma. The subtle plume of material jetting from the sunward side, hints of the dust tail beginning to form. And critically, by comparing images taken days apart, Astronomers could watch the comet evolve, see how its activity changed as it approached the sun, measure the rate at which it was losing mass. James Webb Space Telescope brought different capabilities to bear. Webb, the most powerful infrared observatory ever built, launched in late 2021 and positioned at the L2 Lagrange point, a gravitationally stable location about 1 million miles from Earth, observed 3I's Atlas with its near-infrared spectrograph in late August 2025. Webb doesn't see visible light the way Hubble does. Instead, it sees heat-infrared radiation, the glow of warm objects, and the absorption features of molecules vibrating and rotating. When Webb looked at 3I Atlas, it saw the chemical signatures we discussed earlier: carbon dioxide, water, carbon, monoxide, carbonyl, sulfide, each molecule leaving its distinctive fingerprint in the infrared spectrum. These observations were technically challenging. 3I Atlas was bright enough to observe, but faint enough that long exposures were needed. And because Webb is an infrared telescope, it has to be kept incredibly cold to avoid its own heat contaminating observations. Every observation requires careful thermal management, precise pointing, and complex data processing to extract clean signals from the noise. But from Earth orbit and beyond, other eyes were watching too. The Swift Observatory, a satellite designed primarily to detect gamma-ray bursts, the most energetic explosions in the universe, turned its ultraviolet telescope toward 3I Atlas in late July. Swift's instruments could see wavelengths invisible to human eyes, the ultraviolet light, where hydroxyl ions and water vapor show their strongest emission. The data Swift collected helped confirm the presence of water sublimating from the comet's nucleus, adding another piece to the chemical puzzle. NASA's SPHEREx mission, which had launched earlier in 2025 to map the entire sky in infrared wavelengths, captured observations of 3I Atlas during mid-August. SPHEREx is designed to study distant galaxies and star-forming regions, but its sensitivity made it perfect for detecting the infrared signatures of ice and carbon dioxide in the comet's coma. The mission's data contributed to confirming elevated CO2 levels, helping establish that 3I Atlas's chemistry differed subtly from typical solar system comets. From Mars, multiple spacecraft participated in the observational campaign. NASA's MAVEN, the Mars Atmosphere and Volatile Evolution mission, in orbit around the Red Planet since 2014, has an imaging ultraviolet spectrograph designed to study Mars's upper atmosphere. But in late September 2025, just days before 3I Atlas reached its closest point to Mars, MAVEN turned that instrument toward the comet. What MAVEN saw was extraordinary. The spacecraft captured ultraviolet images showing hydrogen atoms surrounding 3I Atlas, not just from the comet itself, but distinguishable from hydrogen in Mars's atmosphere and hydrogen flowing through interplanetary space. By using a special observing mode that separates sources based on velocity, MAVEN could isolate the comet's hydrogen signature, revealing the cloud of atoms streaming away from the nucleus as water molecules broke apart in sunlight. These observations were particularly valuable because of MAVEN's unique location. From Mars, the geometry was different than from Earth. The angle of viewing changed what was visible, how bright the comet appeared, which parts of the coma were illuminated. And the timing capturing the comet just before its close pass by Mars meant MAVEN saw 3I Atlas at a stage of activity that Earth-based telescopes had missed. ESA's Mars Express and ExoMars Trace Gas Orbiter also contributed observations. The Trace Gas Orbiter carries an instrument called CASIS, the Color and Stereo Surface Imaging System, designed to photograph Mars's surface in high resolution. Pointing a surface imaging camera at a distant comet isn't what the instrument was designed for, but the team made it work, capturing images that helped refine the comet's trajectory. And here's where the story becomes particularly fascinating. ESA's Planetary Defense Team, the Near-Earth Object Coordination Center, used the observations from Mars' orbit to improve predictions of 3I Atlas's path through space by a factor of 10. Not 10%, 10 times more accurate than previous estimates. How? By triangulation, essentially. When you observe an object from two widely separated locations, you get two different perspectives, two different viewing angles. By comparing observations from Earth and from Mars, separated by over 100 million miles, astronomers could measure the comet's position far more precisely than from Earth alone. But there was complexity. Mars itself is moving orbiting the Sun at about 24 kilometers per second. The spacecraft observing from Mars' orbit are themselves moving around Mars. All of these motions had to be accounted for in the calculations. The astronomers had to determine not just where 3I Atlas was, but exactly where their spacecraft was, when it took each observation, then work backward through multiple layers of orbital mechanics to extract the comet's true trajectory. It required collaboration between ESA's flight dynamics, experts, science teams, and instrument specialists. It was the first time astrometric measurements from a spacecraft orbiting another planet had been officially submitted to the Minor Planet Center, the international clearinghouse for such data. A small milestone, but a significant one, demonstrating that interplanetary spacecraft could contribute to planetary defense and asteroid tracking in ways their designers never anticipated. Even NASA's Perseverance rover on Mars' surface got in on the action. Perseverance, whose mission is to search for signs of ancient life in Jezero Crater and collect samples for eventual return to Earth, paused briefly in its exploration to point its Mastcam-Z camera at the sky. The rover captured images of 3I Atlas from the surface of another world, a reminder that our robotic emissaries have become sophisticated enough to opportunistically study transient phenomena, not just their primary targets. Further out in the solar system, spacecraft that had nothing to do with Mars or comets contributed what they could. NASA's Lucy mission, on its way to study Trojan asteroids that shared Jupiter's orbit, used its high-resolution black and white imager, LORI, to capture a series of photos of 3I Atlas between September 15th and 17th. Lucy was 240 million miles away from the comet at the time, but its sensitive camera could still detect the faint visitor. These observations from Lucy served multiple purposes. They provided another data point for trajectory refinement, viewing the comet from yet another angle. They tested the spacecraft's ability to track and image a fast-moving target, valuable practice for when Lucy eventually reaches its asteroid destinations. And they demonstrated the principle that deep space missions can contribute to observing campaigns even when they're far from their primary targets. It's NASA's Psyche. Spacecraft traveling toward a metal-rich asteroid between Mars and Jupiter acquired 4 observations over 8 hours on September 8th and 9th, when 3I Atlas was about 33 million miles from the spacecraft. Psyche's multispectral imager captured data that helped astronomers study the faint coma surrounding the nucleus, contributing to estimates of gas production rates and dust particle sizes. And ESA's JUICE mission, Jupiter Icy Moons Explorer, observed 3I Atlas in October 2025, just after the comet's closest approach to the Sun. JUICE was farther from the comet than the Mars orbiters had been, but it caught the comet at a critical moment, when it was most active, when sublimation was most vigorous, when the chemistry visible in its coma was most representative of the comet's interior composition. Interestingly, the data from JUICE won't be received until February 2026. The spacecraft stores observations on board when communication bandwidth is limited, then downlinks them when higher data rates are available. This delay is normal for deep space missions, where the distance to Earth means communication is slow, and observation data can accumulate faster than it can be transmitted. Scientists are still waiting for that data, still anticipating what it might reveal. Closer to the Sun, spacecraft designed to study our star contributed unexpected observations. NASA's Parker Solar Probe, which repeatedly dives through the sun's corona, studying solar wind and magnetic fields, wasn't positioned to see 3I Atlas directly. But other solar missions were. ESA and NASA's SOHO, the Solar and Heliospheric Observatory stationed at the L1 Lagrange point between Earth and Sun, observed 3I Atlas from October 15th to 26th as the comet passed through SOHO's field of view. SOHO has discovered thousands of comets over its decades of operation, most of them sun-grazing comets that dive close to our star and either evaporate or break apart. But 3I Atlas was different, an interstellar visitor passing through regions of sky that SOHO monitors constantly. NASA's stereo mission, Solar Terrestrial Relations Observatory, consists of 2 spacecraft that orbit the sun at different positions, providing stereo views of solar activity. Both spacecraft captured images of 3I Atlas, with one observing from September 11th to October 2nd. These observations were valuable because they occurred when the comet was behind the sun, as seen from Earth, hidden in solar glare, invisible to ground-based telescopes and most space telescopes. SOHO and stereo could still see it providing continuous coverage during a period when we otherwise would have lost track of the comet entirely. NASA's PUNCH mission, Polarimeter to Unify the Corona and Heliosphere, observed 3I Atlas from September 20th to October 3rd. PUNCH, which launched earlier in 2025, is designed to study the solar wind and how it interacts with the interplanetary medium. When a comet passes through PUNCH's field of view, the instruments can observe how the comet's tail interacts with solar wind, how charged particles are accelerated and deflected, providing insights into both the comet's activity and the local space environment. Despite having observed and discovered thousands of comets over the years, this was the first time NASA's heliophysics missions had purposefully observed an object originating from another solar system. Another milestone in our growing capability to study interstellar visitors. From the ground observatories around the world contributed their own observations. The Gemini telescopes in Hawaii and Chile, twin 8-meter mirrors that together provide coverage of the entire sky, obtained spectra that revealed water ice and helped measure gas production rates. The Very Large Telescope in Chile, with its array of 4 8.2-meter telescopes that can work individually or together, captured the high-resolution spectra that detected nickel and confirmed cyanide. Smaller telescopes contributed too. Amateur astronomers equipped with modern CCD cameras and processing software captured images and astrometry that helped refine the orbit. The discovery of Oumuamua and the subsequent interest in interstellar objects has energized a community of dedicated observers who watch for these rare visitors, contributing data that complements professional observations. This kind of collaboration spanning amateur and professional astronomers, ground and space-based telescopes, missions throughout the solar system, represents something profound about how modern science works. No single observatory or spacecraft could have assembled a complete picture of 3I Atlas. The comet was too faint for some instruments, too bright for others, visible from some locations, but not others observable at different wavelengths from different platforms. Only by pooling observations by each mission and telescope contributing its unique perspective could astronomers build a comprehensive understanding. It's a model of cooperation that transcends national boundaries, institutional rivalries, and individual egos. When something truly interesting appears, the scientific community responds as a community, not as competing factions. And there's practical value in this beyond just studying comets. The coordination developed for observing 3I Atlas serves as practice as rehearsal for scenarios that might matter far more. ESA explicitly noted that the exercise was valuable for planetary defense, for the possibility that someday we might need to track an object that actually poses a threat to Earth. being able to rapidly mobilize assets across the solar system, to share data in real time, to calculate trajectories using observations from multiple vantage points. These are capabilities that could be critical in an emergency. 3I's E-Atlas posed no danger, but observing it honed skills and demonstrated that our infrastructure for planetary defense extends beyond Earth orbit, that we can leverage missions designed for other purposes to contribute to tracking near-Earth objects. Think about what this means for humanity's future in space. We're building not just individual missions, but an ecosystem of sensors and spacecraft that can work together, that can respond flexibly to unexpected events, that collectively form a kind of solar system-wide awareness. We're not there yet. Coverage is still spotty, capabilities are limited, and most of space remains unmonitored. But the response to 3I Atlas showed what's possible when we coordinate effectively. And coordination will only improve. Future missions will carry more sensitive instruments. More countries are launching space programs, adding their capabilities to the mix. Communication networks are improving data sharing, becoming more seamless. The next interstellar visitor, whenever it arrives, will be observed even more comprehensively than 3I Atlas, with even more instruments from even more locations contributing pieces to the puzzle. But there's also something ephemeral, something fleeting about these observational campaigns. They're intense focused, all-consuming while they last, and then they're over. The comet moves on, fading from view, and the spacecraft and telescopes that tracked it return to their primary missions, their regularly scheduled programs. Data analysis continues for years, but the moment of active observation passes quickly. For the scientists involved, there's a bittersweet quality to this. Months or years of preparation coordination, planning all focused on a window of opportunity that lasts weeks or months and then closes forever. You get one chance to observe, one opportunity to capture data, and then the target is gone. No going back for a second look, no repeating an experiment that didn't work the first time. That urgency, that finality makes every observation precious. It drives observers to push their instruments to the limit, to stay up through the night, capturing data, to coordinate across time zones and continents to ensure nothing is missed. Because missing something means it's lost forever, that particular piece of the puzzle permanently unavailable. And yet, they succeeded. The global astronomy community, the network of spacecraft throughout the solar system, the dedicated engineers and scientists who made it all work, they succeeded in capturing an unprecedented data set on 3I Atlas. Not everything, certainly, but enough. Enough to address fundamental questions, to make meaningful comparisons, to advance our understanding of interstellar objects and what they tell us about the galaxy. The hunt continues in laboratories now, in computer models, in careful analysis of spectra and trajectories. But the moment of watching together, of collective attention, focused on one small visitor from far away. That moment builds towards something else, toward understanding not just what we saw, but what it meant to see it at all. There are moments in astronomy when the universe arranges itself into perfect irony, when the thing you most want to see happens at precisely the moment it becomes invisible, when the climax of a billion-year journey unfolds behind a curtain of light so bright it blinds every telescope pointed toward it. October 30th, 2025 was one of those moments when 3I Atlas reached perihelion, its closest approach to our sun burning brightest in its ancient dance with gravity, and we on Earth could see none of it. Perihelion. The word comes from Greek peri, meaning near, and helios, meaning sun. It's the point in any orbit where an object comes closest to the star. It's circling. Except 3I Atlas wasn't circling. It was falling past, swooping by on its hyperbolic trajectory, feeling the full warmth of our sun for the first and only time before climbing back out into the eternal cold. On that day, 3I Atlas passed just 1.4 astronomical units from the sun's surface, about 130 million miles or 210 million kilometers. To put that in perspective, that's just inside the orbit of Mars. Closer than Mars ever comes to the sun, but farther than Earth at its most distant. A middle distance neither scorching like Mercury's perihelion, nor distant like the outer planets. But for a comet that had spent billions of years in the deep freeze of interstellar space, this was an inferno. The irony was exquisite and frustrating in equal measure. From late September through most of November 2025, 3I Atlas was in solar conjunction, positioned in the sky in the same direction as the Sun as seen from Earth. During conjunction, the Sun's overwhelming brightness makes it impossible to observe nearby objects. The glare drowns out everything. It's like trying to see a firefly hovering next to a searchlight. So, at the moment when the comet was most active, when sublimation was most vigorous, when the coma was brightest and the tails were longest, when everything that had been frozen for eons was finally violently returning to gaseous form, we couldn't see it. Earth was on the wrong side of the Sun. We were looking in exactly the wrong direction. But here's where the story becomes beautiful again. We weren't alone in watching. We had positioned other eyes throughout the solar system, and those eyes could see what we could not. Think about what perihelion means for a comet. As it approaches the Sun, the intensity of sunlight increases with the inverse square of distance. Get twice as close, receive 4 times the energy. Get 10 times closer, receive 100 times the energy. This isn't linear, it's exponential, accelerating, relentless. For 3I Atlas, having spent billions of years at temperatures barely above absolute zero, this warming was catastrophic in the most literal sense, a complete transformation, a phase change not just in its physical state, but in its behavior, its appearance, its very nature. The surface that had been frozen solid began to soften, then sublimate. Water ice transformed directly to vapor without passing through a liquid phase. Carbon dioxide, which sublimates at even lower temperatures than water, began venting vigorously. The rate of mass loss, the amount of material streaming off the comet every second, increased dramatically as perihelion approached. Scientists estimate that comets can lose between 1 and 10 tons of material per second at peak activity. That might not sound like much compared to the comet's total mass of hundreds of millions of tons, but over days and weeks it adds up. The comet was quite literally evaporating, sacrificing itself to the Sun's warmth, shedding layers of ancient ice that would never refreeze, never return to the nucleus, dispersing instead into the solar system as individual molecules and dust grains. And as this material escaped, it carried with it the pristine chemistry of the comet's interior. The surface layers, weathered by billions of years of cosmic ray exposure, had been shed. Deeper ice that had been protected since formation was now exposed to sunlight for the first time. The molecules released at perihelion were as close as we would ever get to sampling the original chemistry of the molecular cloud that formed 3I Atlas's parent star system. But from Earth, we could see none of this happening in real time. We could only watch as the comet approached the Sun through September, became lost in solar glare by late September, and disappeared behind our star from our perspective. Fortunately, spacecraft elsewhere in the solar system had different perspectives. From Mars, the geometry was completely different. When Earth, the Sun, and 3I Atlas were aligned with the Sun in the middle, Mars was positioned at an angle where the comet remained visible, not perfectly positioned, but visible enough. The Mars orbiters had already observed the comet in late September, capturing data as it made its closest approach to the red planet on October 3rd, passing within 29 million kilometers. But their instruments remained pointed toward the comet through October, tracking its continued approach to the Sun, even as it vanished from Earth's view. China's Tianwen-1 Mars probe, which has been studying Mars since entering orbit in 2021, captured images of 3I Atlas showing the comet's growing activity. The images revealed the coma, expanding the tail, lengthening clear visual evidence that sublimation was accelerating as the comet approached perihelion. From these observations, astronomers could watch the transformation in real time. The brightness increased not just because the comet was getting closer to the Sun and therefore better illuminated, but because it was intrinsically producing more light, reflecting more sunlight off a larger cloud of dust and gas. The rate of increase in brightness told them about how the comet was responding to heating, how quickly fresh material was being exposed, whether the activity was steady or variable. And the Mars observations revealed something else: jets. Specific plumes of material erupting from discrete locations on the nucleus, visible as bright streaks or fans in the coma. These jets form when sunlight hits particularly active areas on the comet's surface where fresh ice is exposed, or where fractures allow subsurface material to escape more easily. As the nucleus rotates, these active areas move in and out of sunlight, causing the jets to turn on and off to pulse with the comet's rotation period. By tracking how the jets change position and intensity over hours, astronomers could estimate how fast the nucleus was spinning, probably completing one rotation every several hours, though the exact period remained uncertain. The solar observatories SOHO and Stereo captured their own unique perspectives during this period. These spacecraft, designed to watch the sun and its corona, have wide fields of view that include regions very close to the sun in the sky. They routinely observe sun-grazing comets that dive into the solar corona and either survive or disintegrate. 3I Atlas wasn't a sun grazer, it stayed well outside the sun's corona, but it still passed through SOHO's and Stereo's fields of view. The images these missions captured showed the comet as a bright point moving against the much brighter background of the sun's corona, with a tail streaming behind it, pushed by solar wind and radiation pressure. These observations were particularly valuable for understanding the comet's tail structure. The tail of a comet is actually two tails, typically a dust tail made of solid particles that reflect sunlight and an ion tail made of charged gas molecules that glow from ultraviolet excitation. The two tails can point in slightly different directions because they respond differently to forces. Dust particles are pushed away from the sun by radiation pressure, the physical momentum of photons striking the particles. Larger particles are less affected and lag behind, while smaller particles are pushed more vigorously and stream away faster. This creates a curved dust tail like smoke trailing from a moving candle. The ion tail, by contrast, is controlled by the solar wind, the stream of charged particles constantly flowing outward from the sun. Ions in the comet's coma are picked up by the solar wind and accelerated to high speeds, creating a straight, narrow tail that points directly away from the sun regardless of the comet's direction of motion. SOHO and Stereo's observations showed both tails clearly allowed measurements of their lengths, and brightness revealed how they changed as the comet passed through regions of space with different solar wind densities. And because these spacecraft observed continuously, they could watch the tails respond to variations in solar activity. When the sun released a burst of enhanced solar wind, the ion tail would brighten and extend farther, sometimes showing waves or kinks as the disturbance propagated along its length. NASA's Punch mission, observing from its unique vantage point, captured particularly beautiful images of the tail structure during the comet's passage behind the sun. Punch is designed to study the solar corona and solar wind, so it has instruments optimized for detecting faint structures in the bright environment close to the sun. When 3I Atlas passed through its field of view, those same instruments revealed details in the comet's tail that were invisible to other observers. The tail at perihelion stretched for millions of kilometers, possibly over 10 million, though exact measurements were difficult because the tail gradually fades rather than having a sharp endpoint. Material shed from the nucleus at perihelion would remain in the solar system for months or years, slowly dispersing eventually, either falling into the sun or being pushed outward by radiation pressure to join the general interplanetary dust population. In a sense, 3I Atlas was leaving pieces of itself behind. Molecules and dust grains that had been part of the comet for billions of years were now scattered along its trajectory, drifting independently, no longer bound to the nucleus. They would orbit the sun on their own paths, gradually spiraling inward or outward, depending on their size and the balance between gravity and radiation pressure. And this raised an interesting question. If 3I Atlas had passed through our solar system millions of years ago instead of now, and if it had shed material at perihelion, then could some of that ancient interstellar dust still be drifting through space waiting to be encountered by Earth as it orbits the Sun? Probably not from 3I Atlas specifically, the odds are too low, the timescales too uncertain. But from other interstellar visitors over the history of our solar system, over billions of years, yes, possibly. Scientists estimate that we might be continuously sweeping up tiny amounts of interstellar dust particles, remnants of comets that passed through long ago, now so dispersed and mixed with solar system dust that we can't distinguish them. Every time you see a shooting star, a meteor burning up in Earth's atmosphere, there's a tiny, almost infinitesimal possibility that the dust grain that created that flash of light came originally from another star system, was shed by an interstellar comet during some ancient passage, and has been drifting through our solar system ever since, waiting for that moment of final glory. Most shooting stars are definitely from solar system sources, debris from known comets, fragments from asteroid collisions material that's been orbiting the sun for billions of years. But the possibility that some small fraction might be interstellar adds a layer of poetry to the experience of watching meteors. You might be seeing not just our cosmic neighborhood, but a visitor from far away ending its journey in light. At perihelion, the temperature on the sunlit side of 3I Atlas's nucleus would have risen dramatically. Not to melting temperatures, we're still probably talking about well below freezing by Earth standards, but warm enough for vigorous sublimation. Perhaps as warm as -50 or -30 degrees. Celsius may be warmer in the most intensely illuminated spots. That might not sound warm, but remember, this is a comet that has spent most of its existence at temperatures of -270 degrees Celsius. A 100-degree temperature increase might as well be an oven. The thermal shock alone could have caused fracturing cracking of the surface, exposing fresh material that would immediately begin sublimating. Some comets don't survive perihelion. The thermal stress the tidal forces if they pass very close to the sun, the mechanical disruption from vigorous outgassing, all of these can tear a comet apart. We've observed comets fragmenting at perihelion, breaking into multiple pieces that then drift apart, each piece continuing to sublimate until nothing remains but dispersed dust. 3I's Atlas was never in danger of that. Its perihelion distance 1.4 AU was far enough from the sun that tidal forces were negligible and thermal stress, while significant, wasn't catastrophic. The comet survived perihelion intact, though certainly diminished, having shed a noticeable fraction of its mass to space. And as it passed perihelion and began climbing back outward, moving away from the sun on the outbound leg of its hyperbolic trajectory, the activity began to decline. Not immediately, there's a thermal lag, a delay between when heating occurs and when the effects show up. The interior of the nucleus takes time to warm and time to cool again. But gradually over days and weeks, the rate of sublimation decreased, the coma contracted, the tails grew fainter and shorter. The comet was returning to dormancy, refreezing, settling back toward the state it had been in before entering the inner solar system, though changed now lighter, having sacrificed layers of its ancient ice to our sun's warmth. By early November, it began to re-emerge from behind the sun as seen from Earth. Astronomers eagerly trained their telescopes on it again, curious to see how it had changed, whether perihelion had altered its behavior in noticeable ways. And indeed, the comet looked different, dimmer than before, conjunction, but still active, still sporting a visible coma, still releasing gas and dust, though at a declining rate. Hubble captured new images on November 30th, showing the comet post-perihelion, allowing comparison with pre-perihelion observations. The nucleus appeared intact. The coma was still present but less extended. The dust tail remained visible but was shortening as production rates decreased. These post-perihelion observations are valuable because they allow astronomers to measure how quickly a comet deactivates how deeply the heating penetrated, whether there are changes in the rotation state or chemical composition visible in the coma. Sometimes perihelion passage exposes layers with different chemistry, or causes the nucleus to crack and reveal fresh ice, or changes the rotation period if outgassing is asymmetric enough to act as torque. For 3I Atlas, the post-perihelion behavior appeared relatively normal, a comet behaving like comets do, gradually settling down as it moves away from the sun's warmth. No dramatic outbursts, no unexpected fragmentations, no mysterious changes in chemistry. Just a natural, predictable response to thermal cycling. And yet, there was something profound about having witnessed this moment even indirectly, even through instruments stationed at Mars and solar observatories that happened to be looking the right direction. This was the climax of 3I Atlas's passage through our solar system. The point of maximum activity, maximum brightness, the moment when this ancient wanderer came as close as it ever would to resembling what it might have been billions of years ago, orbiting its parent star. For a brief time perhaps, just days at the peak, 3I Atlas was transformed from a frozen dormant time capsule into an active evolving dynamic system, from an object that had barely changed in eons into something that was changing by the hour, shedding mass, rearranging itself, responding to forces it hadn't felt since it left its home system. And then inevitably that moment passed. The transformation reversed. The comet began its long return to dormancy, carrying with it now slightly less mass, slightly different surface characteristics, slightly altered by its brief encounter with warmth. Have you ever watched something precious slip away, knowing you'll never see it again? Felt that mixture of gratitude for having witnessed it at all, and sadness that it's already becoming memory rather than present experience? That's what perihelion felt like for the astronomers, tracking 3I Atlas, a moment they had anticipated for months, witnessed as best they could with the tools available, and now watched recede into the past, never to be repeated. The comet continues outward activity, declining, brightness, fading, but the moment of transformation, that brief burning at perihelion, when billions of years of frozen patience met. Present warmth, that moment is already history, already passing into the realm of data to be analyzed rather than events to be witnessed. Sometimes the most interesting thing about a discovery isn't what we find, but what we convince ourselves we're seeing. Sometimes imagination moves faster than data speculation, drowns out careful measurement, and the story we want to tell becomes louder than the truth trying to be heard. In July 2025, as astronomers work to understand 3I Atlas through patient observation and rigorous analysis, another narrative emerged not from the comet itself, but from our ancient human tendency to see agency where there is only physics intention, where there is only chance. On July 16, 2025, just 2 weeks after the comet's discovery, astrophysicist Avi Loeb and researchers from the Initiative for Interstellar Studies published a paper on Archive, a preprint server where scientists share research before peer review, proposing that 3I Atlas might be an extraterrestrial spacecraft, not a natural object, not a comet formed by accretion in a protoplanetary disk billions of years ago, but something built, something sent, something that chose to come here. The hypothesis rested on several claims about 3I Atlas's characteristics that the researchers considered anomalous. The comet appeared larger than expected for an interstellar object. It seemed to show a deficit of identifiable chemicals in early spectra, and most dramatically, its trajectory appeared to be aligned with the solar system's ecliptic plane in a way they calculated as statistically improbable for a random interstellar visitor. The paper made waves immediately. News outlets picked up the story. Headlines appeared, suggesting that we might be witnessing our first confirmed alien technology passing through the solar system. Social media erupted with speculation, debate, excitement, and skepticism in equal measure. And the scientific community responded swiftly, firmly, and almost unanimously to push back against these claims. Astronomer Chris Lintott was among the first to criticize the hypothesis, publicly noting that the overwhelming consensus among researchers actually studying 3I Atlas was that it behaved exactly like a natural comet. The science news website Live Science reported that many researchers were disappointed with Loeb's paper, feeling it distracted from the actual scientific work being done to characterize the comet's chemistry and trajectory. Several astrophysicists, including science communicators Scott Manley and David Kipping, pointed out significant flaws in the statistical analysis used to assess the trajectory's alignment with the ecliptic. The calculation of probability, they argued, involved questionable assumptions and selective framing that made a fairly normal trajectory appear artificially unusual. This wasn't the first time Loeb had proposed that an interstellar object might be alien technology. He had made similar suggestions about Oumuamua in 2017, arguing that its unusual elongated shape and slight but measurable acceleration could be explained if it were a light sail, an artificial structure designed to catch solar radiation for propulsion. That hypothesis had also been widely disputed by other astronomers, who pointed out that natural explanations, outgassing from the object's surface for instance, could account for the observations without requiring technological origins. And before Oumuamua, Loeb had suggested that a meteor detected in 2014 designated Cienios 2014-0108 might have been an interstellar object and possibly artificial, despite significant uncertainty in the data used to classify it. A pattern had emerged. When something unusual was detected, or when normal objects could be framed as unusual through selective emphasis, Loeb would propose an extraterrestrial technology hypothesis. And each time the broader scientific community would respond that natural explanations remained far more plausible. To be fair, Loeb himself acknowledged the likely outcome. He wrote in his blog that the most probable conclusion would be that 3I Atlas is a completely natural interstellar object, probably a comet, but he defended his approach as an interesting exercise in its own right, fun to explore irrespective of its likely validity. And there's nothing inherently wrong with exploring unlikely hypotheses. Science progresses partly through bold speculation, through entertaining possibilities that seem remote but aren't strictly impossible. The problem arises when speculation is presented in ways that suggest equivalence with evidence-based conclusions, when hypothetical scenarios are given weight they haven't earned through rigorous testing. Astronomer Samantha Lawler highlighted this issue in her response. She noted that while remaining open-minded about testable predictions is important, Loeb's paper pushed that sentiment to its limits. The evidence presented, she said, was absolutely not extraordinary, and extraordinary claims require extraordinary evidence. That phrase, extraordinary claims, require extraordinary evidence, is often attributed to Carl Sagan, though the concept has deeper roots in scientific philosophy. It captures an important principle. The more unusual a claim, the more surprising it would be. If true, the stronger the evidence needs to be before we should accept it. Claiming that 3I Atlas is a comet is an ordinary claim. We've observed thousands of comets. We understand how they form, how they behave, what chemistry to expect. Finding another comet, even one from an interstellar origin, requires only ordinary evidence. Spectra, showing water and carbon dioxide, a coma and tail behavior consistent with sublimating ice, a trajectory explained by gravity. All of this is exactly what we'd expect and requires no special pleading. Claiming that 3I Atlas is alien technology is extraordinary. It would be the first confirmed detection of extraterrestrial intelligence, the most significant discovery in human history, proof that we're not alone in the universe. Such a claim demands overwhelming evidence observations that cannot possibly be explained by natural phenomena, signatures that unambiguously indicate artificial construction patterns that scream intelligence rather than merely whispering ambiguity. and the evidence for 3I Atlas being artificial was questionable statistical arguments about trajectory early measurements that were later refined and showed nothing unusual, and an apparent size estimate that was largely an artifact of the bright coma obscuring the actual nucleus. Let's examine each of these claims in detail, because understanding where they fall short teaches us something important about how science evaluates unusual hypotheses. The trajectory argument suggested that 3I Atlas's path through our solar system was suspiciously aligned with the ecliptic plane, the flat disk in which Earth and the other planets orbit. If the comet were arriving from a random direction in interstellar space, the reasoning went, it should be equally likely to approach from any angle. The fact that it came in relatively aligned with our planetary system seemed too convenient, too targeted. But this analysis had problems. First, the alignment wasn't nearly as precise as it was made to sound. 3I Atlas's orbit is inclined about 25 degrees to the ecliptic, not perfectly aligned, but not perpendicular either. And second, the calculation of how improbable this alignment was depended heavily on how you define the question. If you ask, what's the probability that this specific object would arrive at this specific time from this specific direction, you'll always get a tiny number because any specific event has low probability when you frame it narrowly enough. But if you ask, what's the probability that sometime in the next century an interstellar object would be detected with an orbital inclination less than 30 degrees, the answer is quite different, much more reasonable, much less suggestive of anything unusual. This is a version of what statisticians call the Texas sharpshooter fallacy. Imagine someone fires a gun randomly at a barn, then walks up afterward and paints a target around the tightest cluster of bullet holes, claiming to be an expert marksman. You can't calculate the probability of a specific outcome after the fact and treat it as though it were predicted in advance. Scientists studying 3I Atlas's trajectory found no evidence of anything but natural gravitational motion. The path was precisely what you'd expect for an object on a hyperbolic orbit, approaching from interstellar space, swinging past the sun and continuing outward. No course corrections, no deviations from Newtonian mechanics, no thrust or maneuvering that would indicate propulsion. The size argument was similarly flawed. Early estimates suggested 3I Atlas might be several kilometers across, which would indeed be unusually large for an interstellar object. But those estimates were based on the comet's total brightness, including its coma. As we discussed earlier, distinguishing the nucleus from the surrounding cloud of dust and gas is difficult, and early measurements almost always overestimate nucleus size. As more detailed observations accumulated, particularly from Hubble, the size estimates were revised downward dramatically. By August 2025, astronomers had constrained the nucleus diameter to somewhere between 440 meters and 6 kilometers, with the true size likely at the smaller end of that range. This is not unusual. This is comparable to 2I Borisov, and entirely consistent with what we'd expect for natural comets. The chemical argument that 3I Atlas showed a deficit of identifiable chemicals was based on very early, very preliminary spectra, taken when the comet was still far from the sun and relatively inactive. As it approached perihelion and sublimation increased, the chemistry became much clearer. Water carbon dioxide, carbon monoxide, cyanide, nickel, carbonyl, sulfide molecule after molecule was identified, building up a chemical portrait entirely consistent with a natural comet. There was nothing missing, nothing anomalous, nothing that required anything other than straightforward interpretation as ice and rock sublimating under solar heating. So, why did the alien hypothesis gain so much attention? Why did it spread through news media and social media, despite having such weak support from actual evidence? Partly, it's because the hypothesis is exciting. The possibility of alien technology is inherently more interesting to most people than another comet, however scientifically valuable that comet might be. Headlines about potential alien spacecraft get clicks. They generate engagement. They tap into deep human curiosity about whether we're alone in the universe. Partly it's because the hypothesis came from a credentialed scientist at a prestigious institution. Loeb is a professor at Harvard, former chair of Harvard's astronomy department, a respected researcher with legitimate contributions to astrophysics. When someone with those credentials proposes something, it carries weight with journalists and the public, even if other scientists in the same field are skeptical. And partly it's because the hypothesis was published during a particular moment of public attention. The discovery of 3I Atlas happened to coincide with a 43-day U.S. government shutdown that affected NASA's ability to comment publicly on the comet or release images and updates. In that information, vacuum speculation flourished. Online rumors circulated that NASA was hiding something, that the comet was being tracked secretly, that there were reasons the government wasn't talking about it. When NASA finally held a briefing after the shutdown ended, one of the first things they addressed was setting the record straight. NASA Associate Administrator Amit Kshatriya stated explicitly that 3I Atlas is of natural origin, not an example of extraterrestrial technology. The briefing shared observations from over 20 missions throughout the solar system, presenting a comprehensive scientific portrait that left no room for reasonable doubt about the comet's natural character. But by then, the narrative had already spread. The alien hypothesis had already been amplified through countless articles, videos, and social media posts. And while the scientific community had moved on, satisfied that the question was settled, the speculation continued in corners of the internet, where skepticism of scientific consensus is fashionable. This pattern, scientists reaching consensus while public debate continues, is frustratingly common. It happened with Oumuamua, where the overwhelming majority of astronomers concluded it was a natural object, while popular discussion continued to entertain alien origins. It happens with climate science, with vaccines, with evolution, with any topic where clear scientific evidence conflicts with what people find emotionally appealing or ideologically convenient. The lesson here isn't that we should never speculate about extraordinary possibilities. It's that speculation needs to be proportional to evidence and clearly labeled as speculation when that's what it is. When a hypothesis has been examined by the scientific community and found wanting, when natural explanations account for all observations without requiring exotic assumptions. Continuing to promote the extraordinary hypothesis becomes misleading rather than intellectually courageous. Carl Sagan, who popularized the search for extraterrestrial intelligence and spent his career thinking seriously about how we might recognize alien technology if we encountered it, also warned against wishful thinking masquerading as science. He advocated for keeping an open mind, yes, but not so open that your brain falls out, as the saying goes. Evidence matters. Rigor matters. The difference between possible and probable matters. Could 3I Atlas be an alien spacecraft? Could it be a probe sent by an ancient civilization arriving in our solar system? After billions of years of travel, its technology so sophisticated that it mimics natural processes perfectly. Could it be designed to look like a comet to release water and carbon dioxide to sublimate ice in exactly the pattern we'd expect from solar heating, all to avoid detection or study our response? Yes, technically those scenarios are possible. They're not forbidden by known physics, but they require layers upon layers of assumptions, each of which makes the hypothesis less likely, each of which adds complexity without explanatory power. Natural comet origin requires no assumptions beyond what we already know comets do. The chemistry matches, the behavior matches, the trajectory matches. Everything makes sense without invoking anything new or unusual. This is the principle of Occam's razor when multiple explanations fit. The evidence preferred the simplest one, the one that requires the fewest additional assumptions. It's not that the simplest explanation is always right, but it's the best starting point. The null hypothesis we should accept unless evidence pushes us towards something more complex. And for 3I Atlas, there's no evidence pushing us anywhere. The comet behaves exactly like a comet. Every observation confirms that interpretation. The alien hypothesis adds nothing but complexity, explains nothing that natural processes don't already explain, and makes predictions that aren't borne out by observation. So, why does this matter? Why spend time discussing a hypothesis that scientists have already dismissed? Because it teaches us something about how to evaluate claims, how to distinguish signal from noise, how to recognize when excitement about a possibility has outpaced the evidence supporting it. These skills matter far beyond astronomy. They apply to understanding health claims, political assertions, historical revisionism, any domain where people might have incentives to promote narratives that aren't well supported. Science isn't about being closed-minded or refusing to consider new ideas. It's about proportion, matching the strength of our conclusions to the strength of our evidence. It's about updating beliefs when new data arrives, but not prematurely jumping to conclusions based on ambiguity and wishful thinking. 3I Atlas is remarkable enough without needing to be artificial. It's the third interstellar object we've confirmed, a messenger carrying information about stellar systems, billions of years old, a physical sample of chemistry from parts of the galaxy we'll never visit. That's extraordinary. That's precious. That's worth studying with every instrument we can point at it. We don't need to invent mystery where the actual mystery, the genuine wonder of how planets form, how comets scatter into interstellar space, how the galaxy distributes matter and chemistry across billions of years is already profound and beautiful and real. Sometimes the truth is more beautiful than the fantasy. Sometimes understanding what something actually is reveals depths that imagination alone couldn't reach. And sometimes the most important discovery is learning to distinguish between what we hope to see and what's actually there, between the stories we tell ourselves and the stories the universe is telling us if we listen carefully enough. There's a particular quality to goodbyes when you know they're final. Not see you later or until next time, but the kind of farewell that carries the weight of never. The kind where you watch something slip beyond the horizon, knowing it will never curve back, never return, never offer a second chance to say what you meant to say, or see what you missed the first time. December 19th, 2025 marks that kind of goodbye when 3I Atlas reaches its closest point to Earth, still impossibly distant, and begins the final acceleration that will carry it beyond our ability to follow, beyond our capacity to wonder about it as anything other than memory. On that day, the comet will pass approximately 1.8 astronomical units from our planet. That's about 170 million miles, or 270 million kilometers, nearly twice the distance from Earth to the Sun. In cosmic terms, this is not close. You could fit the entire orbit of Venus between us and the comet with room to spare. If you were somehow standing on 3I Atlas on that day, Earth would appear as a pale blue dot, barely distinguishable from the background stars. No brighter than Venus looks to us on a clear evening. And yet, this is as close as the comet will ever come to us. This is the moment of nearest approach, the point where two trajectories ours, circular and predictable, traced year after year around our sun, and the comet's hyperbolic and unrepeatable passing through just once, come closest to intersecting without ever actually touching. Think about the geometry of this encounter for a moment. 3 eyes. Atlas approached our solar system from the depths of interstellar space, its path determined by billions of years of gravitational interactions, with stars and gas clouds we'll never identify. It entered the region where our sun's gravity is strong enough to curve its trajectory, swinging inward past Jupiter's orbit, past Mars, reaching perihelion in late October, then climbing back outward on the opposite side of the sun from where it entered. Earth, meanwhile, continues its steady orbit, taking 365 days to circle the sun, once predictable as clockwork, unchanging in its pattern. We happened to be on the far side of our orbit when the comet reached perihelion, which is why we couldn't see it during its moment of maximum activity. And now, as the comet moves outward and we continue our circle, there's this one moment, this brief window on December 19th, when the distance between us reaches its minimum, before beginning to increase again, inexorably, forever. It's like two trains passing in opposite directions. There's a moment when they're closest, when passengers in both trains could theoretically look out their windows and see each other, and then they're moving apart, and no amount of wishing or wanting can bring them back together, because they're on different tracks, heading to different destinations, operating under different rules. By December 19th, 3 BUAs, Atlas will have changed from the object discovered in July. It will be dimmer, less active its coma, contracted as sublimation, slows in the cold of the outer solar system. The tails that stretched millions of kilometers at perihelion will be shorter, fainter, harder to detect. Observations will require longer exposures, larger telescopes, more sophisticated processing to extract the faint signal from the noise of the night sky. And even with our best instruments, there will come a point, probably sometime in 2026, perhaps early 2027, when the comet becomes too faint to track. When even Hubble and Webb, even the largest ground-based telescopes, can no longer gather enough photons to distinguish the comet from the countless dim galaxies and distant stars that fill the same region of sky. It won't disappear suddenly. It will fade gradually, appearing fainter in each successive observation, until one day astronomers will point their telescopes at the predicted location and find nothing they can confidently identify as the comet. Just the background sky, the cosmic ocean of faint light against which the comet has become indistinguishable. And that will be it. The last observation, the final data point. The moment when 3i Atlas passes beyond the reach of human instruments and returns to being an object we know exists but can no longer see, can no longer study, can only remember and wonder about. After that point, the comet will continue accelerating as it climbs out of the sun's gravitational well, not accelerating in the sense of adding velocity from thrust, but shedding the speed it gained, falling inward, returning gradually to the velocity it had when it arrived. Eventually, probably sometime in the late 2020s or early 2030s, it will cross back over the boundary where our sun's influence becomes negligible compared to the general gravitational field of the galaxy, and it will be truly interstellar again. And it will carry with it something it didn't have before, a change subtle but real in its trajectory. The sun's gravity bent, the comet's path curved it, altered its direction without changing its speed. Where it's going now is different from where it was going before it encountered us. Not dramatically different. The angle change is measured in degrees, maybe tens of degrees, not a complete reversal, but different enough that its future path through the galaxy will be altered. Billions of years from now, when 3i Atlas completes another orbit around the galactic center, it will be in a slightly different location than it would have been if it had never passed through our solar system. The gravitational nudge from our sun will have consequences that ripple forward through time, changing which stars the comet passes near, which molecular clouds it transits through, where in the galaxy it ends up eons hence. We touched it in a way. Not physically, but gravitationally. We left a mark on its trajectory, subtle and impersonal, the inevitable consequence of gravity acting between masses. And in exchange, it left a mark on us, not gravitationally, because its mass is too small to affect Earth's orbit in any measurable way, but intellectually, scientifically, philosophically. We learned things from 3i Atlas that we couldn't have learned any other way. We confirmed that interstellar comets can be detected and studied with current technology. We measured the chemistry of material from another stellar system directly, not through telescopic spectroscopy of the distant stars, but through analysis of reflected sunlight from ice and dust, just hours or days, removed from a nucleus we could observe in detail. We demonstrated that global coordination of astronomical assets, ground telescopes, space telescopes. Interplanetary missions can respond effectively to unexpected events, that we can mobilize our observational capabilities to study rare phenomena when they appear. We practice skills that might someday be critical for planetary defense, for tracking objects that could pose actual threats rather than benign visitors like 3I Atlas. And we were reminded yet again of the importance of distinguishing between evidence and speculation, between what we observe and what we imagine, between the universe as it is and the universe as we might wish it to be. But beyond the technical knowledge and the scientific data, 3I Atlas gave us something harder to quantify, a sense of connection to the larger galaxy. A reminder that our solar system is not isolated, but part of a dynamic ecosystem where matter and energy constantly flow between the stars. We are not alone, not in the sense of intelligent life. We still have no evidence for that, but in the sense of being part of something larger, something ancient, something that unfolds on scales both spatial and temporal that dwarf human experience. Every element heavier than hydrogen and helium in your body was forged inside a star that exploded billions of years ago. That's not metaphor, that's literal truth. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was synthesized through nuclear fusion in stellar cores, then dispersed into space by supernovae, then incorporated into clouds of gas and dust that eventually collapsed to form new stars and planets. You are made of stardust. That phrase has become cliché, repeated so often it's lost some of its power. But encountering an object like 3I Atlas makes it visceral, again makes it real. Here is dust and ice from another stellar system, carrying elements that were processed through different stars, that condensed in a different molecular cloud, that never had anything to do with Earth, or our sun, or us, until pure chance brought it passing through our neighborhood. And yet, the chemistry is familiar. Water is water, whether it formed here or there. Carbon dioxide is carbon dioxide. The molecules don't care where they came from. They obey the same physical laws, form the same structures, sublimate at the same temperatures, regardless of which star they once orbited. This universality, the fact that physics and chemistry work the same way everywhere, is one of the deepest and most reassuring discoveries of modern science. It means that what we learn studying objects here applies to objects everywhere. It means the universe is comprehensible, knowable, governed by consistent principles rather than arbitrary local rules. And it suggests that the conditions necessary for life, liquid water, organic chemistry, energy sources are not unique to Earth. Not special results of an improbable coincidence, but common outcomes of physical processes that occur wherever stars form and planets coalesce. Whether life actually arose elsewhere, whether intelligence developed, whether civilizations exist that could build the spacecraft Loeb imagined when he looked at 3I Atlas, those questions remain unanswered. But the chemistry is there. The building blocks are there. The potential is there, woven into the fabric of the galaxy itself. 3I Atlas is leaving now, carrying that potential with it, frozen once again, as it returns to the cold of interstellar space. The surface that was briefly warmed at perihelion will refreeze. The sublimation that created the coma and tails will cease. The molecules that escaped into our solar system will remain behind, scattered along the comet's trajectory, while the nucleus, diminished but intact, continues its journey alone. Where is it going? We can calculate the trajectory with reasonable precision for the next several thousand years, predicting which direction it's heading, though not exactly where it will end up. The comet is moving outward from the sun at an angle inclined about 25 degrees from the plane of our planetary orbits, heading generally toward the constellation as Lynx, as seen from Earth, though of course it will be billions of years before it gets anywhere near even the closest stars in that direction. Computer simulations can extend the trajectory farther, accounting for gravitational influences from nearby stars, from the galaxy's overall structure, from dark matter, whose distribution we only partially understand. These simulations become increasingly uncertain as you look farther into the future, small uncertainties in present velocity, and position compound over time into large uncertainties about distant future location. But one thing is certain, 3I Atlas will not return to our solar system. Its trajectory is hyperbolic unbound. It's leaving forever, and nothing short of a close encounter with another star's gravity well will curve its path enough to bring it back. And even if such an encounter occurred, even if billions of years hence the comet was deflected into a trajectory that coincidentally aimed it back toward our sun, we wouldn't be here to see it. The sun will have evolved. Earth's orbit might be unstable. Humanity, if we still exist, will be unimaginably changed. So, this is goodbye. Final and absolute. We saw it, we studied it, we learned what we could, and now we watch it go. There's a melancholy to that, isn't there? The way beautiful things are often temporary, the way the most precious moments are the ones that can't be repeated. If 3I Atlas orbited our sun, if it were a regular periodic comet like Halley's, we could wait and see it again. Generations could witness its returns. It would become familiar, predictable, almost mundane. But because it's passing through just once, because this encounter is unique and unrepeatable, it carries a weight that regular comets don't. This is our only chance. These months in 2025 and early 2026 are the only time in all of human history, past and future, when 3I Atlas will be close enough to study. Miss this opportunity and it's missed forever. And yet, there's also something freeing about impermanence. The fact that this is temporary makes it precious. The fact that we can't hold on to it forever makes the time we have more meaningful. We don't take it for granted precisely because we know it's leaving. Maybe that's true of everything we value. Maybe the finality of farewell is what teaches us to pay attention while we can. As 3I Atlas fades from our telescopes, as the data collected during its passage through our solar system continues to be analyzed in laboratories and universities around the world, as papers are published and knowledge accumulated and our understanding of interstellar objects deepens, we can take comfort in knowing that we witnessed something rare, something that may not happen again in our lifetimes. We were here. We looked up. We saw a visitor from the depths of space and time. And for a brief moment measured against the eons of the comet's existence, we connected with something ancient and far away. The universe is vast beyond comprehension. The time spans involved in cosmic processes are so long, they mock human intuition. And yet sometimes rarely the vastness arranges itself into moments of connection. A comet from another star system happens to pass close enough to ours that curious creatures on a small blue planet can point instruments at it and read the messages written in its ice. What are the odds? 1 in billions, 1 in trillions. Does it even make sense to calculate probabilities for unique historical events? Perhaps it's enough to simply acknowledge that it happened, that we were lucky enough to be here when it did. That for all the suffering and confusion and difficulty of human existence, we live in an era when we can reach beyond our atmosphere, can study objects millions of miles away, can decode the chemistry of distant worlds and find in them echoes of our own origins. 3I Atlas is leaving, but what it taught us remains. The data persists, the understanding grows, and somewhere, perhaps another interstellar visitor is already on its way, will arrive years or decades or centuries from now. And when it does, we'll be better prepared to study it because of what we learned from this one. The universe keeps sending messengers. Our task is to keep watching, keep learning, keep reading the messages they carry. Sleep well, friend. Dream gently. And know that even now, in the darkness between the stars, ancient travelers are drifting, carrying stories. We're only beginning to learn how to read. Thank you for staying with me through this journey. Thank you for listening to this story, told softly about science and wonder, and the beautiful impermanence of rare encounters. There are more stories waiting in the darkness, more visitors approaching from depths we can barely imagine. And when they arrive, when the next messenger passes close enough to see, We'll be here to watch together, to wonder together, to learn what secrets the cosmos has decided to share. Until then, rest. The night is long and filled with stars. Good night.